Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most quietly terrifying and strangely beautiful ideas in all of science. We'll drift through the invisible fabric that holds everything together, an ocean of fields humming softly beneath reality. And we'll ask a simple question with a breathtaking answer. Could the universe itself be unstable? Could everything we know, from the atoms in our bodies to the light of distant galaxies, rest on a cosmic knife's edge, waiting for one final change? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always a joy to imagine all the corners of the earth where these words are quietly playing, each of us in our own little pocket of time. Now feel free to dim the lights, maybe turn on a fan for that soft background hum, and let's gently begin our journey into Did We Just Discover the Universe's Greatest Weakness, together. And if your mind begins to wander somewhere along the way, that's perfectly fine. Let it drift. The universe has waited billions of years for this story. It can wait a little while longer for you. Imagine sitting in a dim lecture hall late in the evening. The air feels thick with the warmth of half-closed notebooks and cooling coffee. A tall, bespectacled man stands before a blackboard already crowded with symbols, his expression part mischief, part quiet wonder. He adjusts his glasses, looks at his students, and says, "Not only God knows, I know, and by the end of the semester, you will know." That man was Sydney Coleman, physicist, joker, and reluctant prophet of doom. He claimed he never enjoyed teaching, but his enthusiasm was electric. Students said his lectures felt less like lessons and more like doors quietly opening in the mind. His colleagues called him the physicist's physicist. Even Sheldon Glashow, a Nobel laureate himself, once said, "He's kind of a major god." Coleman laughed easily, joked often, and had a gift for turning the strangest corners of quantum theory into something almost comforting. And yet, beneath the charm and wit, he carried an idea that was anything but comforting. In the late 1970s, he discovered something extraordinary and quietly horrifying. A mathematical way to destroy the entire universe. He didn't mean through war or weapons or any human hand. He meant that the universe itself, the vacuum that cradles every atom, every star, every breath, might not be truly stable. Reality, he realized, could be like a ball resting not at the lowest point in its valley, but caught on a ledge, high above a deeper abyss. One small shift, one quantum tremor could send that ball rolling, and in that instant every law of physics would change. It's difficult to imagine an end without noise, without warning, without light. Yet that's exactly what Coleman's equations implied. At any point in space, at any moment in time, a tiny bubble of lower energy could appear, like a single spark that doesn't shine but instead erases. The bubble would race outward at the speed of light, rewriting the rules of existence as it passed. There would be no pain, no panic, no awareness, because everything that could feel or think would vanish in the same heartbeat. To many physicists, this was both absurd and strangely poetic. The universe, vast and ancient, ending not with fire but with silence, folding in on itself because of a simple imperfection hidden in its design. But Coleman's insight was not fantasy. It came from the same set of equations that explain why matter exists at all. The standard model of particle physics, the quiet grammar of the cosmos. He had joined a long lineage of thinkers who had already peeled back layer after layer of nature's disguise. Before him came Maxwell, who showed that electricity and magnetism were not separate at all, but part of one shimmering field. Then came Einstein, who linked energy and mass in his simple relation, that energy equals mass multiplied by the speed of light squared, a phrase that would make the stars and the atoms kin. Coleman's era, however, belonged to the language of the quantum field. In that language, everything, light, matter, even empty space, is alive with vibration. There are no solid particles, only ripples in invisible oceans. What we call an electron is merely a small repeating pattern in one vast field. A photon, a wave of light, is the brief shiver of another. The universe is a sea of overlapping melodies, and what we perceive as matter is just the rhythm we happen to hear. Coleman loved that idea. He once told his students that the most mysterious thing about quantum physics was not its uncertainty, but its consistency. Everything dances, he said, but the dance never misses a beat. That was the strange beauty of the Standard Model. Beneath all the chaos, there was exquisite order. But even perfect choreography can hide a flaw in the stage, and so Coleman began to ask, what if the stage itself, the empty vacuum, was not the true ground, but only a temporary flaw? If everything we call stable was simply waiting for a lower note, a truer silence? The thought was almost unbearable, even to him. Yet the equations refused to let go. They whispered that the Higgs field, the same gentle field that gives matter its mass, might be balanced precariously, like that pencil teetering on its tip. He would later write, in a tone both scientific and tragic, that if such a collapse began, there would be no warning at all. The bubble of new vacuum would rush across space at nearly the speed of light, so that even the fastest signal could never escape it. The last moment of our universe would be peaceful only because nothing would remain to notice. Strangely, Coleman never dramatized his own discovery. He mentioned it the way one might describe the weather: fascinating, inevitable, and not particularly personal. He kept his humour until the end, saying once that physics had taught him how to take the universe less seriously. But the world of physics took him very seriously indeed. His insight would echo through the decades, shaping how scientists understood not only the Higgs field but the fragile nature of existence itself. As we drift further into the story, keep this image close: the calm surface of a pond that may not be as still as it seems. Beneath it lies an invisible tension, a quiet potential for change so vast that, if released, it would rewrite the sky. That tension is what we now call the metastability of the universe, a word that sounds clinical, but behind it lies the oldest question of all: how safe is reality, really? In July of 1945, deep in the New Mexico desert, the horizon bloomed into light. For the first time in history, the Earth felt the heartbeat of a man-made sun. The physicists who had worked for years on this secret project watched in stunned silence as a fireball rose into the dawn, turning the sand beneath it into glass. Among them was Robert Oppenheimer, who quietly recalled a line from an ancient text: "Now I am become death, the destroyer of worlds." Next to him stood Kenneth Bainbridge, the project's test director. When the roar of the explosion finally reached them, Bainbridge turned to Oppenheimer and said, half in awe and half in regret, "Now we're all sons of bitches." It was a sentence soaked in both triumph and shame, and it lingered in the dry morning air long after the shockwave had passed. The bomb had worked. Humanity had found a way to unbind the energy that holds matter together. In that moment, science had crossed a line it could never uncross. The same equations that described the dance of particles had been turned into instruments of fire. Oppenheimer would later say that physicists had known sin, not in the religious sense, but in the quiet realization that their curiosity had outpaced their wisdom. When the war ended, the men and women who had built the atomic age were left with a strange emptiness. They had seen what their equations could do when harnessed by politics and fear. For years they had worked under the weight of secrecy, unable to share ideas freely, their work stamped with classifications and code names. In 1947, they decided to meet again, not to build anything, not to weaponize knowledge, but to reclaim the simple joy of understanding. That gathering took place on a small island off the coast of New York. Shelter Island, they called it, as if physics itself needed a refuge. The attendees read like a roll call of 20th century brilliance. Richard Feynman, Julian Schwinger, Robert Oppenheimer, John Wheeler, and many others who had carried the torch of theory through the dark years of war. The air buzzed not with radiation this time, but with the pent-up energy of minds finally free to wander again. Julian Schwinger, formal and precise, lectured first. His equations ran across the board like calligraphy, mapping the invisible conversations between electrons and light. Then came Feynman, younger, restless, and full of mischief. Where Schwinger saw lines of algebra, Feynman saw little drawings, loops and arrows that traced how particles might meet, exchange, and part again. He scribbled these strange doodles as he spoke, the audience half amused, half bewildered. They would later call them Feynman diagrams, and they would change the way the world calculated the unseen. To most of us, the universe seems made of things: stones, air, light, our own hands. But in that room, a new picture was forming. The physicists were beginning to see the world not as a collection of objects, but as a set of relationships, constantly shifting and humming. Two electrons did not repel each other because of an invisible force pushing them apart. Instead, they exchanged a tiny messenger of light, a photon, like two dancers passing a note between them as they spin. The idea was breathtakingly simple and impossibly strange. Every interaction in nature could be described as the sharing of these invisible messengers. The strong force that binds the atomic nucleus relied on gluons. The weak force that allows certain atoms to decay relied on heavier couriers called W and Z bosons. Even gravity, still mysterious, seemed to whisper that it too might have a messenger particle, though none had ever been found. At Shelter Island, this vision began to take form. The world was no longer made of solid bits of matter, but of fields stretching through space and time, rippling whenever something happened. A particle was no longer a marble, it was a localized vibration, a shiver in a field that covered everything. The vacuum, what we once thought of as empty space, was now seen as the stage that never went dark, its surface alive with quiet tremors. And yet, just as the physicists began to celebrate this harmony, a new puzzle appeared. The equations predicted that most of these messenger particles, the ones carrying the weak force, should have no mass at all. They should flit across the universe as freely as light. But in reality, the W and Z bosons were heavy, so heavy that they could only travel a distance smaller than the width of a single proton before fading. It was as if light itself had suddenly learned to crawl instead of fly. The mystery was not a small one. It cut to the heart of the standard model, the framework that explained everything they could test. If these bosons were truly massive, something had to be giving them that mass. The universe was hiding a mechanism, a quiet hand shaping its most fundamental particles. The clue came from a connection few expected, a link between mass and the fleeting uncertainty of quantum mechanics. According to Heisenberg's principle, the shorter the time you have to observe something, the less certain you can be about its energy. The universe, in a sense, borrows energy to allow short-lived particles to exist, but it must pay that energy back almost instantly. The heavier the particle, the shorter its lease on life. For the weak force, this meant that its messengers, the W and Z, could exist only for unimaginably brief moments, and could move only tiny distances before dissolving back into the vacuum. The heavier they were, the shorter their reach. It was this property that made radioactive decay such a local, intimate phenomenon, whispering only across atomic distances rather than cosmic ones. To put it another way, light can travel forever because its messenger, the photon, has no mass, but the weak force dies young because its messengers carry the burden of weight. This was the paradox that would eventually lead to the discovery of the Higgs field. But in 1947, no one yet knew that a new kind of field, a soft, scalar ocean spread evenly across space, was waiting to explain everything. They could only sense that something invisible was missing, something that tied together all the disparate notes in the cosmic symphony. After the conference, the physicists returned to their universities and laboratories, invigorated. Feynman would go on to win the Nobel Prize for his diagrams, Schwinger for his equations. Theoretical physics entered its golden age, a time when the chalk dust of a lecture hall could alter the way we saw the stars. But in that same decade, another seed was planted, one that would eventually bloom into Sydney Coleman's dreadful realization. The more precisely they mapped the universe, the more they saw that its balance was fragile. Equations that looked eternal might only describe a temporary calm. If we follow the thread a little further, the story begins to deepen. For hidden beneath the beauty of symmetry was an even greater secret, that the universe we know might have been born from a moment when perfection broke, when balance itself decided to fall. If you were to keep zooming inward, leaving behind the streets and rooftops of your city, then the cells of your skin, then the swirling shells of your atoms, you would enter a world that doesn't quite behave like anything you've ever seen. It's a place without edges or surfaces, where matter is less like a solid thing and more like music. The deeper you go, the less the universe looks like a machine and the more it resembles a melody being played on invisible strings. Physicists call this the realm of quantum fields. But to understand it, it helps to set aside the image of billiard balls bumping into one another. Imagine instead an ocean so vast that it fills everything, even the emptiness between the stars. The water of that ocean is invisible, but it vibrates in countless ways. Every vibration, every ripple, every fleeting wave pattern represents something we call a particle. In this view, an electron isn't a tiny sphere spinning through space. It's a little shimmer in the electron field, one that repeats over and over like a wave in deep water. A photon, the particle of light, is simply a brief ripple in another field, the electromagnetic field. Even the protons and neutrons in the heart of every atom are not truly solid. They are made of smaller ripples called quarks, tied together by still more ripples in a field of their own, the strong force field. Everything is fields, layered and interwoven like overlapping waves on a calm sea. When the ripples of one field interact with those of another, we see forces. When ripples stay confined within a small space, we see matter. In truth, the universe is a vast concert of vibrations, where energy and matter are just different notes played on the same, invisible instrument. You might wonder why we don't notice this ocean. After all, we're made of it. But like fish that never realize they're swimming in water, we too are immersed in the sea of fields. The reason you feel the world as solid is simply that these ripples refuse to overlap in certain ways. When you press your hand against a wall, the fields of your atoms meet the fields of the wall's atoms, and the quantum waves refuse to merge. What you feel as resistance, what you call solid, is just the universe saying, softly but firmly, no farther. Richard Feynman once described it this way: when two electrons approach each other, it isn't that they sense each other directly, or that there's an invisible thread connecting them. Each is a ripple in the electron field. Their presence creates new ripples in the electromagnetic field, and those new ripples, photons, carry energy and momentum back and forth. The electrons exchange these silent couriers, and in doing so, they push each other away. That's what the electric force really is, an endless swapping of tiny packets of light. It's a delicate choreography that happens everywhere, all the time. In the light streaming through your window, in the warmth of your skin, in the tiny hum of your phone battery, countless particles are sending these messengers back and forth, never touching yet, always connected. It's the quiet conversation that holds the universe together, For the physicists at Shelter Island and beyond, this realization was both humbling and exhilarating. The world was no longer built from Lego-like blocks, but from endless, fluid exchanges. And within this language of fields, another mystery began to appear: the question of mass itself. If fields fill all of space, and particles are just waves in those fields, then why do some of those waves carry weight, while others glide effortlessly? Light waves move without rest, forever massless. But electrons, quarks, and the particles that carry the weak nuclear force seem to drag through the vacuum as though it were honey. Something in the emptiness of space gives certain waves resistance, a kind of cosmic friction. To visualize this, imagine walking through a crowded room. If the room is full of people who know you, they stop you, shake your hand, ask questions, slow you down. You gain inertia. If the room is full of strangers who barely notice you, you move through freely, almost as if you're weightless. That's roughly how mass works in the quantum field view. It depends on how strongly each particle interacts with another invisible field, the Higgs field. But the Higgs field itself wouldn't be discovered until decades later. For now, the physicists could only sense its absence, like hearing a harmony that isn't played yet somehow shapes the music. They knew the equations demanded something, a mechanism that would give mass to the W and Z bosons without breaking the beautiful symmetry of their theory. It was a missing piece of an elegant puzzle. Meanwhile, the broader structure of the Standard Model was taking shape. It included two great families, the fermions, which make up the stuff of matter, and the bosons, which carry the forces. The fermions included quarks and leptons, tiny ripples that combine to form everything solid and everything fleeting. The bosons were the messengers, the photon for light, the gluon for the strong force, and the W and bosons for the weak force. And somewhere, perhaps, a graviton for gravity, if gravity could ever be woven into the same quantum tapestry. The beauty of it all was that these fields obeyed precise symmetries, patterns that stayed the same even when shifted or rotated in abstract ways. Physicists believed that symmetry was not just decoration, it was the very language of reality. And yet, somewhere in that perfect symmetry, mass appeared. Something was breaking the stillness. The more they explored, the more they found hints that the vacuum itself, the so-called empty background, was not truly empty at all. Even at absolute zero, it shimmered with quantum noise. Tiny particles flickered into and out of existence too quickly to see, borrowing energy from nothing and returning it before the universe could notice. It was this restless vacuum that would one day prove central to Coleman's terrifying conclusion. The physicists didn't know that yet. They were simply chasing patterns, listening to the rhythm of equations that hinted at hidden unity. To them, it was a golden age, a time when mathematics and imagination walked hand in hand. They had not yet glimpsed the shadow that would fall across that harmony, the realization that even the most perfect field might be temporary. For now, the quantum world seemed stable, eternal, and endlessly fascinating. It was a place of ripples and whispers, not of doom. But as we drift further into the story, that calm surface will begin to tremble. Somewhere in those silent equations lies a question that has no easy answer. What if the very ocean of reality itself could one day evaporate? If we follow the thread a little further, the story of mass and mystery takes us into one of the strangest forces in nature, the weak force. The name makes it sound harmless, as though it were the quiet sibling of gravity or electromagnetism. Yet in truth, the weak force plays a role far more dramatic. It is the architect of transformation itself, the force that allows one kind of particle to turn into another, that lets stars shine and atoms die. Without it, the sun would never burn and we would never exist. Physicists once thought of forces as push and pull, like invisible strings tugging between particles. But in the quantum view, a force is more like a fleeting exchange, a secret handshake between two ripples in the field, The weak force, however, is different. It doesn't simply connect particles, it changes them. It can take a down quark and turn it into an up quark, transforming a neutron into a proton. In doing so, it releases an electron and a neutrino, allowing the atom to shift its identity ever so slightly. This subtle change is what makes radioactive decay possible, what lights up nuclear reactors and fuels the fires of the stars. But for all its importance, the weak force hides behind an extraordinary limitation. Its reach is almost impossibly small. While the electromagnetic force can stretch from one side of the galaxy to the other, the weak force can barely cross the heart of an atom. It's as if the universe built a force meant for whispering, not shouting. The question was why? Why should this powerful agent of transformation be confined to such a tiny range? The answer, physicists discovered, lay in its messengers, the W and Z bosons. These were the heavyweights of the subatomic world, particles nearly 100 times more massive than a proton. And in quantum physics, mass comes with a price: range. The heavier the messenger, the shorter the distance it can travel before fading away. To understand this, imagine the vacuum of space as a vast savings account of energy. According to the rules of quantum mechanics, the universe is allowed to borrow some of that energy to create a particle out of nothing, but only for an instant. The larger the amount borrowed, the faster it must be paid back. So, for a lightweight messenger like the photon, which carries light and has no mass, the loan is effortless. It can travel forever. But for the weak forces, massive W and Z bosons, the energy debt is enormous, and the repayment is almost immediate. They appear, act, and vanish again in a blink far shorter than any human thought could measure. That fleeting existence is why the weak force fades after only a trillionth of a meter. It's as if it tries to speak but can manage only a whisper before dissolving back into silence. At first, physicists accepted this as one of nature's oddities, but the deeper they looked, the stranger it became. The Standard Model, the grand equation that described all the known particles, was built on the idea of symmetry. Each field and particle followed rules that mirrored one another, a hidden balance as elegant as a snowflake. In that perfect symmetry, all the messengers of nature should be weightless, like the photon. Yet somehow, 3 of them had gained immense weight. Something had broken the symmetry. Something unseen had chosen favourites, giving mass to some particles but not to others. To illustrate what that meant, picture a perfectly still pond on a windless morning. Drop a pebble into it, and circular ripples spread evenly in all directions. That is symmetry. But now imagine the pond begins to freeze unevenly. The ripples slow, distort, and finally stop in one direction before the other. The symmetry is gone, and the pond has chosen a shape. The question facing physicists was, what in the universe had tilted that balance? The search for an answer would stretch over decades, drawing in thinkers from every corner of the scientific world. Some turned to the mathematics of gauge theory, the study of how local perspectives can change without altering the underlying truth. They imagined fields that could twist and rotate in abstract spaces, preserving the same physics no matter how one viewed them. It was a beautiful framework, one that captured the unity between electromagnetism and the weak force. But it had a flaw. If the theory remained perfectly symmetrical, all particles should remain massless. In other words, symmetry alone was too perfect to allow reality as we know it. Then came a series of insights that would quietly revolutionize physics. Scientists like Abdus Salam, Steven Weinberg, and Sheldon Glashow realized that perhaps the universe wasn't perfectly symmetrical after all. Maybe it had once been, in its earliest moments, but something had caused that perfection to shatter, something that would later be called spontaneous symmetry breaking. At first, this phrase sounds abstract, even cold. But its meaning is deeply poetic. It suggests that the universe began in perfect harmony. every field and force indistinguishable from the rest. Then, as the cosmos cooled and expanded, it chose a particular state, like a spinning top that begins to wobble and finally fall to one side. That single decision, if we can even call it a decision, gave mass to particles and structure to matter. From that fall came everything that would ever exist. One can think of it as a kind of cosmic crystallization. At high energies, the universe was a fluid of pure symmetry, featureless and bright. As it cooled, patterns began to form, forces separated, particles gained identities, and matter emerged from what was once uniform light. The moment that symmetry broke was, in a sense, the first act of creation after the Big Bang. Still, the mystery wasn't solved. What exactly caused the symmetry to break? What was the field or mechanism that made the W and Z bosons so heavy while letting light remain free? That answer would come from a quiet man in Scotland, a physicist so modest he would later flee to a pub on the day he won the Nobel Prize. But his idea, born in the 1960s, would change not just the weak force but our understanding of reality itself. It would reveal that space is not truly empty, and that every atom in the universe moves through an invisible ocean of energy that gives it substance. As our story drifts toward that moment, the tone shifts from mystery to revelation. The puzzle of the weak force, whispered through radioactive decay and stellar fire, was guiding science toward a profound truth. Emptiness itself is alive, and through it, the universe found a way to give weight to its own light. The story now carries us from the quiet whisper of the weak force into the dream that has guided physics for more than a century, the dream of unity. The idea that behind all the diversity of nature, all the winds and lights and storms of the cosmos, there might be a single pattern, a single law, a single heartbeat. The search for that hidden unity began long before the word quantum was ever spoken. It began in a time of ink and candlelight with a Scottish physicist named James Clerk Maxwell. In the mid-19th century, electricity and magnetism were known but separate, like two instruments playing different melodies. Electric charges could produce sparks, magnets could pull at iron, and yet no one knew why these two phenomena seemed to echo each other in strange ways. Maxwell looked at the experiments of Michael Faraday, who had shown that a moving electric charge creates a magnetic field, and that a changing magnetic field in turn induces electricity. It was as if these two forces were calling back and forth across the void. Maxwell translated that intuition into mathematics, 4 elegant equations that would come to define electromagnetism. But there was something deeper hiding in them. When he rearranged his equations, he found that they predicted waves, ripples of electric and magnetic energy travelling through space. When he calculated their speed, the number astonished him. It was the same as the measured speed of light. In a single stroke of chalk, light was no longer a mystery separate from its electricity and magnetism. It was the marriage of the two, the electromagnetic wave, a rhythm of one creating the other, endlessly. Light, it turned out, was simply the visible whisper of electric and magnetic fields dancing together in harmony. That discovery became the first great unification in physics. It taught scientists that nature rewards those who look for symmetry and connection. If two forces as different as lightning and magnetism could be shown to be one and the same, what other hidden relationships might the universe hold? Decades later, the same longing for unity guided a new generation of physicists. Among them were 3 men whose paths would cross in the second half of the 20th century: Abdus Salam, Steven Weinberg and Sheldon Glashow. Their dream was to bring together the weak force and electromagnetism, the two forces that govern almost everything that happens in atoms. It was not an easy path. The weak force seemed awkward and asymmetrical, full of strange rules and short ranges. Electromagnetism, by contrast, was clean and infinite in reach. To unify them, Salam, Weinberg and Glashow turned to a new kind of mathematics, one that dealt not just with shapes or numbers, but with the transformations that leave certain properties unchanged. This was the language of symmetry in its purest form, the foundation of what are called gauge theories. The idea can sound abstract, but its heart is simple. Imagine standing in a vast field of tall grass. Each blade can lean in any direction, but what matters to you is not the direction itself, but how each blade's tilt compares with its neighbours. The pattern of differences is what defines the landscape. In physics, gauge symmetry works the same way. The specific orientation of the fields, the direction of the invisible arrows that describe them, can change from place to place, as long as the overall relationships remain consistent. The rules of nature care about the harmony, not the absolute notes. This insight, though mathematical, was deeply aesthetic. It meant that the laws of physics are written in a language that stays beautiful no matter which perspective you choose. Shift the viewpoint, and the equations still sing the same tune. At the heart of this understanding stood another genius, one who never built an accelerator or led a laboratory, but instead worked quietly in the realm of pure mathematics, Emmy Noether. She was born in Germany in 1882, at a time when women were not expected, nor often allowed, to contribute to theoretical science. Yet she was unstoppable. Noether discovered a connection so profound that it became the backbone of modern physics. Every symmetry in nature corresponds to a conservation law. That simple sentence holds the universe together. Because time moves smoothly forward, energy must be conserved. Because space looks the same no matter where you stand, momentum is conserved. Because the equations of electromagnetism stay unchanged when you rotate them in a certain abstract way, electric charge is conserved. Noether's theorem, though we won't call it by that stiff name here, revealed that the universe's sense of balance isn't arbitrary. It's built into its very foundations. Symmetry is the reason things last, the reason motion continues, the reason energy can flow without disappearing. It is the geometry of existence. Decades later, the unifiers, Salam, Weinberg and Glashow, stood upon this elegant foundation. They used the language of symmetry to propose that electromagnetism and the weak force were really two aspects of one deeper interaction. The challenge was to find the right kind of symmetry that could encompass both. They found it in a pair of intertwined patterns, one simple, one more complex. If Maxwell's equations described a circle of symmetry, a rotation around a single axis, then Salam and his colleagues discovered that nature's next pattern was more like a sphere, where every point represents a possible internal state of the particles. They imagined that all particles could shift within this invisible sphere, changing identities without breaking the rules of physics. At high energies, such as those that fill the newborn universe, the symmetry of this spherical pattern would be perfect. The weak and electromagnetic forces would be indistinguishable, merged into one seamless field. But as the universe cooled, that symmetry would falter. A new field would emerge, one that would tilt the balance and separate the forces, just as cooling water forms ice crystals that break the uniform stillness. That field, though no one yet knew it by name, would one day be called the Higgs field. It would be the unseen background that gave identity to particles, weight to matter, and substance to space itself. There's a quiet irony here. In chasing the dream of perfect symmetry, scientists discovered that reality depends on its imperfection. It's the breaking of symmetry, the moment the balance slips, that gives rise to everything we see. The stars, the planets, our own breath, all born from a cosmic stumble. The great unifiers never described it that way. They spoke in equations and group structures, in rotations and couplings. But behind their formal words lay something simple and profound, the belief that the universe is intelligible because it is beautiful. As our quiet exploration turns to the next step, the story will shift from the abstract elegance of symmetry to the fragile moment when that elegance failed. From that failure came weight, form, and the first sense of gravity pulling at the newborn cosmos. The next discovery would show that in falling out of balance, the universe found its shape and its fate. The path now carries us toward the moment when symmetry, the elegant balance that physicists had admired for generations, finally broke. And from that break, everything familiar was born. Imagine the early universe just a heartbeat after the Big Bang. There were no stars yet, no light, no atoms, not even the faint idea of a shape. Space was thick with energy, an ocean of heat so intense that all the fields of nature shimmered as one. In this state, the weak and electromagnetic forces were still indistinguishable. The cosmos was a featureless blur, a bright fog of perfection. But perfection cannot last. Even the most delicate balance can tremble. As the universe expanded, its temperature dropped, and the great ocean of fields began to cool. When that happened, something unexpected stirred, an instability, a tiny imbalance that would eventually change everything. To visualize this, imagine a perfectly balanced pencil standing upright on its tip. In theory, it could stay that way forever, the forces of gravity and pressure perfectly aligned. But in reality, the smallest vibration, the drift of a molecule of air, the sound of a whisper, will cause it to fall. The pencil doesn't choose where to fall, but once it does, the symmetry is gone. One direction becomes special. The Higgs field behaved in just that way. At first, it was perfectly balanced. Its value everywhere was zero, calm and featureless. But as the cosmos cooled, that equilibrium became unstable. The field could no longer stay perfectly upright. It fell, taking on a small, non-zero value everywhere in space. The universe had broken its symmetry, and in doing so, it gave birth to mass. When physicist Peter Higgs first wrote down this idea in the summer of 1964, he wasn't sure it mattered. In fact, he wrote to a colleague, "I think I've discovered something useless." But the uselessness he spoke of would one day win him the Nobel Prize and explain why matter exists at all. Higgs had realized that the empty space of the universe is not truly empty. It is filled with an invisible energy field, a quiet hum that vibrates in every corner of the cosmos. When certain particles move through it, they interact with this field, and that interaction slows them down, just as a swimmer feels the drag of water. The stronger the interaction, the heavier the particle appears to be. Particles like photons, which carry light, glide through untouched. That is why light is weightless and can travel forever. But particles like electrons, quarks, and the carriers of the weak force feel resistance as they move through this field. The Higgs field makes space sticky for them, giving them what we call inertial mass, the property that resists acceleration, the reason it takes more effort to push an elephant than a mouse. In one elegant motion, the Higgs mechanism explained the puzzle that had haunted physics for decades. How the W and Z bosons, the messengers of the weak force, could be so heavy when the photon was not. When the Higgs field fell into its new state, it mixed and reshaped those particles, giving the W and Z their mass and leaving the photon free. From that moment onward, the world had structure. Forces separated, particles gained identity, and the universe became a place where things could exist rather than merely vibrate. It's strange to think that imperfection created everything. The breaking of symmetry was not a mistake. It was the universe's first creative act. In the instant the Higgs field fell, the cosmos gained texture. It became a place where some directions mattered, where some particles could hold together while others drifted apart. You could say that the universe found its personality in that moment. Before symmetry broke, it was an unbroken hum of potential, too uniform to be interesting. Afterward, it became capable of contrast, light and dark, matter and energy, attraction and repulsion. Every star, planet and breath you take traces its lineage back to that single imbalance. The Higgs field's fall is often described in terms of potential energy, but we can think of it more gently as a change in landscape. Before the fall, the Higgs field rested at the peak of a hill, perfectly centred but precarious. Afterward, it rolled into a valley, settling in a new position of stability. That valley's floor corresponds to the vacuum expectation value of the field, the average energy that fills all of space, even when nothing else is there. But instead of saying it that way, imagine it as the quiet hum that never stops, the gentle background music to which all matter moves. And yet, not all parts of the symphony are played at once. Some particles, like the ones inside protons and neutrons, owe only a small portion of their mass to the Higgs field. The rest comes from the ceaseless dance of energy within, the tug of the strong force binding quarks and gluons together. Inside, every proton is a storm of movement, tiny flashes of energy constantly appearing and disappearing. Through Einstein's simple truth, that energy and mass are two forms of the same thing, that storm becomes weight. So even here, there is a certain irony. The field that gives mass to the universe is not the sole author of it. Most of the mass that makes you, arises from motion and binding energy, from the restless rhythm inside each atomic heart. The Higgs field provides the stage, the strong force plays the music. When Peter Higgs published his paper, few people noticed. The idea was so subtle that many physicists dismissed it as a mathematical curiosity. Decades would pass before it gained the recognition it deserved. Higgs himself remained shy and self-effacing, avoiding fame as if it embarrassed him. He preferred long walks and quiet reflection to interviews or headlines, but the universe does not care about publicity. The Higgs field had already done its work billions of years before anyone thought to name it. Every atom, every galaxy, every heartbeat depended on that invisible backdrop, and would continue to do so for as long as the cosmos endures. When we think of creation, we often imagine explosions and light. But sometimes creation begins with a fall, a collapse of symmetry, a surrender of perfection. The Higgs field's quiet tipping gave the universe something far greater than balance. It gave it form, resistance, and the slow grace of matter moving through time. As we drift further along this path, one question begins to whisper from beneath the surface of it all. The Higgs field fell once, long ago. But what if it could fall again? What if the valley where it rests is not the lowest one? If there is a deeper valley somewhere, invisible and unreachable, then the universe we know might be living on borrowed balance. And one day, that balance could shift again. Our quiet exploration now turns to the texture of existence itself, the way everything you touch, see, and feel has weight, resistance, and a kind of slow patience. We call that quality mass. And while the word sounds ordinary, it's one of the most remarkable features of the universe. Without it, there would be no gravity, no atoms, no rhythm of cause and effect. Things would not collide, hold together, or drift gracefully through space. They would simply slip away like light through a window. To understand mass, it helps to imagine the Higgs field not as a formula, but as an atmosphere, invisible yet everywhere. Wherever you go in the universe, you're moving through it. It doesn't push or pull you the way air does. It's quieter than that. But it gives you a kind of cosmic drag, a gentle resistance to being moved. When you walk, lift your hand, or even breathe, the particles that make up your body are wading through this universal sea. The way each kind of particle interacts with the field determines how heavy it feels. Some particles, like the photon, slip through untouched. They move at the ultimate speed, light speed, because the Higgs field barely notices them. Others, like electrons or quarks, cling more tightly, feeling the viscosity of space itself. The more they interact, the more they resist being accelerated, and that resistance is what we interpret as mass. It's like walking through different kinds of water. A goldfish moves easily in a bowl, A swimmer glides through a pool, but a diver in thick syrup would find every motion slow and heavy. The field doesn't add mass the way clay adds weight to a sculpture. It changes the way particles behave. Mass isn't an amount of stuff. It's a measure of how stubborn a particle is when you try to change its motion. Peter Higgs once compared it to a crowded room. Imagine a person trying to cross a party where everyone recognizes them. They're constantly stopped, greeted, surrounded by clusters of conversation. They move slowly, weighed down by attention. Now imagine a stranger who enters unnoticed. They pass through effortlessly, almost invisible. The crowd is the Higgs field. The level of attention is the coupling strength, the degree of interaction that gives a particle its mass. In that sense, empty space is anything but empty. It is a living medium, like air dense with invisible whispers. When physicists describe the vacuum, they no longer mean nothingness. They mean the lowest energy state of this field, a calm surface that still hums faintly, never truly still. Every particle in existence moves through this quiet storm. The way the field imparts mass is subtle. It doesn't grab particles like a hand. It influences them through interaction. In the equations that describe it, there is a term representing the field's constant value everywhere in space. That value acts like a silent partner in every particle's motion, gently changing its behaviour. To say it simply, the Higgs field tells the universe how hard it should be to move things. What's extraordinary is how uniform this field is. It doesn't fade with distance or weaken near stars. It stretches smoothly across the entire cosmos, from the spaces between your atoms to the farthest galaxies. In that way, it's like gravity's quiet mirror. While gravity pulls everything together, the Higgs field defines how much effort that pulling requires. When we talk about the mass of an object, say a rock or a mountain or a planet, we're really talking about the sum of millions upon millions of these microscopic interactions. Each quark and electron, each field fluctuation, contributes to the overall resistance of matter. Yet even that isn't the whole story. For inside the protons and neutrons that make up atoms, there's another layer of mystery. Most of their mass doesn't come from the Higgs field at all. It comes from motion. The quarks inside are never still. They swirl and collide, bound together by the strong nuclear force. That constant dance of energy, according to Einstein's relation between energy and mass, becomes weight. In simple words, the heaviness of matter is not the weight of its parts, but the energy of their dance. So when you lift a stone, you're feeling not the weight of solid material, but the pressure of invisible energy confined inside it, the restless heartbeat of the strong force and the resistance of the Higgs field woven together. The universe, it turns out, is built not from things but from interactions, tiny negotiations between what moves and what resists. Physicists have measured the Higgs field's quiet background value. It corresponds to an energy level so vast that it underlies the existence of every atom. But it's best not to think of it as a number. Think of it instead as the soft glow beneath all other lights, the steady hum that never turns off. Every step you take, every thought you have, occurs within that hum. The field's very existence also brings a strange kind of reassurance. Because it's uniform and pervasive, the universe behaves the same way everywhere. A hydrogen atom in a distant galaxy vibrates with the same rhythm as one here on Earth. That shared stability is what allows chemistry, life, and even time as we know it to exist. And yet, buried in that comfort is a question that humbles every physicist who contemplates it. Why this strength? Why this particular value of the field and not another? If the Higgs field were slightly stronger, the universe might have collapsed into dense knots of matter. If it were slightly weaker, atoms could never hold together. Between those two impossible worlds lies a narrow window where everything works, where stars shine, and water flows, and life can breathe. The precision of it all feels almost fragile. It's as if the universe tuned itself like a violin, and somehow the string has stayed in pitch for billions of years. But physicists know how delicate that tuning might be. The equation suggests that the Higgs field's valley, the energy state it fell into after the Big Bang, might not be the absolute lowest one. There could be a deeper valley hidden beyond our reach. If that were true, then everything we call stable would merely be balanced in a temporary lull, like a cup resting on a tabletop that itself floats above an unseen drop. Sydney Coleman, decades after Higgs first proposed his idea, would be the one to explore that possibility in depth. His calculations would reveal that the field we depend on, the very glue of existence, might not be eternal. For now, though, imagine the field around you as a soft wind. Every particle in your body feels it, responds to it, moves through it. This invisible medium gives shape to your world, and as long as it stays steady, so does everything else. But beneath that serenity lies a question whispered by the cosmos itself. What if the field ever wavered again? What if, after holding its breath for 14 billion years, the universe exhaled? From here, the story opens into one of the quietest yet most humbling realizations in all of physics, that most of what you think of as you isn't actually made of you at all. It's made of energy, restless, unseen, and eternal. When you look down at your hand, it feels solid, definite, a small portion of matter carved out of space. You can see it, touch it, move it. But if we peer beneath the skin, beneath the molecules, beneath the atoms that make up those molecules, the picture changes. The atoms are mostly empty space, tiny nuclei surrounded by clouds of electrons that never truly stop moving. Inside those nuclei sit protons and neutrons, and inside them, smaller still, are quarks bound together by the strong nuclear force. But here is the astonishing part. If you add up the masses of those quarks, they contribute only about 1% of the total weight of a proton. The rest, 99% of the mass of everything you touch, see and are, comes from something else entirely. It comes from motion. Inside each proton, the three quarks swirl endlessly, held together by a blizzard of massless particles called gluons. The gluons don't just hold the quarks together, they constantly flicker in and out of existence, trading energy like dancers passing sparks between their hands. The quarks themselves also appear and vanish, creating pairs of quark and antiquark that exist for moments too brief to imagine. This storm of activity means that the inside of every proton, every neutron, every atomic core is a place of furious energy. And according to Einstein's simple relation, where energy and mass are two sides of the same reality, that energy is the proton's mass. You don't need to write the equation. It's enough to remember that every ounce of matter is energy waiting to be recognized. So when you step onto the ground, the weight you feel pulling you down is not the weight of solid things, but of motion, the trapped energy of countless particles racing in tiny circles, kept in place by the strongest force known in nature. It's a beautiful kind of irony. We imagine ourselves as solid, unmoving beings, yet everything that gives us substance comes from restless motion and invisible tension. You are, in a very real sense, a pattern of energy pretending to be still. This realization also changes how we see the Higgs field's role. The Higgs gives the basic ingredients, the quarks and electrons, a small portion of their mass, the foundation on which everything else is built. But the strength of the strong force does most of the heavy lifting. The Higgs field gives the universe its structure, while the strong force gives it its weight. Inside each atom, the two work together seamlessly. The Higgs defines how the particles interact, how they resist movement, and how the field of empty space becomes sticky for some and transparent for others. The strong force then wraps that structure into tight knots of energy, ensuring that matter can exist as something tangible, Without the Higgs, nothing would have mass and particles would zip around at light speed, never forming atoms. Without the strong force, matter would collapse into nothingness, unable to bind. The universe would be an endless sea of ghostly light, no planets, no stars, no eyes to see them. It's easy to forget how much of existence depends on delicate balances like this. We live in the overlap between two great forces, the one that gives weight and the one that holds it together, and it's only in that overlap that complexity and life can exist. Physicists have spent decades exploring this hidden structure, using massive machines that smash protons together at nearly the speed of light. Inside those collisions, the energy of motion briefly converts into pure mass, new particles, fleeting and strange, that tell us how the universe behaves at its deepest level. When those collisions happen, it's as if a tiny piece of the early universe reappears, a spark of that original seething chaos when all fields were hot and tangled. For the briefest instant, symmetry is restored, and then it collapses again as the particles cool and decay. Out of those experiments, the Higgs boson was finally seen, its faint signature confirming what Higgs and others had imagined half a century before. But even after that discovery, questions linger. The equations that describe the Higgs and the strong force are astonishingly precise, yet they hint at fragility. They suggest that the universe is balanced on an edge between stability and collapse, a delicate midpoint between two impossible worlds. The Higgs field, for all its elegance, might not be sitting at the true bottom of its potential. It could be resting in what physicists call a false vacuum, a local minimum of energy that looks stable from within, but hides a deeper valley below. The field fell once when the universe cooled after the Big Bang, breaking symmetry and giving us mass. But it might fall again someday if the right conditions appear. Sydney Coleman would later explore this possibility in exquisite detail, but even before his work, some physicists suspected that this might be the case, that perhaps the world we know is not the final version of reality, only a temporary one. If that sounds unsettling, it's because it is. The Higgs field has held steady for over 13 billion years, but the equations leave room for doubt. One day, at some distant point in space, it could slip into a lower state. If that ever happened, a new kind of universe would begin inside the bubble that formed, a universe with different laws, different forces, and no room for the things we know. And yet, thinking about this doesn't need to be frightening. It's also deeply humbling. It reminds us that everything solid, mountains, oceans, even our own bones, is made from movement and uncertainty, from invisible forces that hold together just long enough for us to notice. When you rest your hand on a table, you're feeling centuries of cosmic choreography beneath your palm, the strong force humming inside atoms, the Higgs field giving texture to space, and the gentle pull of gravity anchoring everything together. You're never truly still, you're participating in an endless performance. The next time you feel your own pulse, think of it as an echo of that ancient dance, the energy that keeps protons whole, that gives you weight, that ties you to the universe. You're a pattern of vibrations assembled by chance and balanced by physics so precise it borders on poetry. And as we drift toward the next step of our story, we'll follow the thread from this balance of energy and matter into the deeper question it raises. If the universe is balanced, how stable is that balance really? What if all this order, this beauty is only temporary? A fleeting calm in an ocean that still remembers how to roar? The trail of clues now leads us to the late 1970s, to a quiet office filled with papers, blackboards, and the faint hum of fluorescent light. Sydney Coleman sits at his desk, the same man whose humour could light up a classroom and whose mind could turn equations into poetry. He's older now, but still animated by that restless curiosity, the need to understand not just how the universe works, but how stable it really is. By this time, the Higgs mechanism had been proposed for more than a decade. It was widely accepted that the field gave mass to particles, that it had fallen into a calm valley after the chaos of the Big Bang. Physicists assumed this valley was the true ground of reality, the lowest possible energy state, the resting point of the cosmos. But Coleman, always skeptical of comfort, wondered whether the story ended there. He began to examine the mathematics of fields and their energy landscapes, those invisible hills and valleys that define how the universe organizes itself. Each valley represents a possible vacuum, a version of reality with its own set of rules. In principle, the universe should settle into the lowest valley it can find. But what if, Coleman asked, it didn't? What if, instead, it stopped halfway down, caught in a hollow that only looks like the bottom? To picture this, imagine a landscape at night. You roll a marble down a hill, and it comes to rest in a shallow dent. From where you stand, it seems still, unmoving, at peace. But if you could see farther, if you had light enough to glimpse beyond the ridge, you'd notice that the dent sits above a deeper valley hidden in shadow. The marble isn't truly stable, it's just stuck, waiting for the tiniest tremor to push it over the edge. That, Coleman realized, might be our universe. The Higgs field, the one that gives mass to everything, could be resting not in the true vacuum of a lowest energy, but in a false one, a kind of cosmic plateau that only feels permanent. The universe as we know it might be living on borrowed balance, a momentary pause between creation and collapse. The thought unsettled even him. He'd spent years teaching that quantum mechanics allowed for probabilities, for uncertainty, for the occasional strangeness that makes physics both maddening and beautiful. But this was different. This was the suggestion that reality itself was temporary, that at any point in space, at any moment in time, the vacuum could choose to change its mind. Coleman described the idea calmly, almost playfully in his lectures, but behind the calm was a breathtaking truth. If the Higgs field ever tunneled from its false vacuum to a true one, it wouldn't happen slowly. It wouldn't crack or rumble or warn us. It would begin at a single point, somewhere in the infinite vastness, and from that point a bubble of lower energy would form, expanding outward at nearly the speed of light. Everything within its path would cease to exist in the form we know. He didn't say this to frighten anyone. He was, at his core, fascinated by the elegance of it, the way the same laws that create stars could also contain their undoing. Physics, he believed, was not a story of comfort but of truth. And sometimes, truth has sharp edges. Coleman's insight drew on decades of earlier work about how systems can escape local minima, how things that seem trapped can still change. The mathematics of such transitions, called quantum tunneling, had already explained why the sun shines. Inside the heart of a star, hydrogen atoms fuse into helium because their quantum waves overlap and penetrate barriers that classical physics would call impenetrable. That same mechanism, he realized, might apply not just to atoms, but to reality itself. He began to imagine what that would mean for the universe. The Higgs field, spread across all of space, might one day undergo a similar transition, not in response to heat or pressure, but through the random, probabilistic tremor of quantum uncertainty. The field could tunnel from one vacuum state to another, from the false to the true. And when that happened, the laws of physics as we know them would rewrite themselves. It is difficult to grasp how sudden and total that change would be. Coleman once explained it by saying, at any moment, at any point in space, reality could begin to change. There would be no noise, no light, no signal travelling faster than the bubble's edge. Everything, the atoms in our bodies, the orbits of planets, the structure of space itself, would be rewritten in the same instant. Yet he spoke of it not as an apocalypse, but as an inevitability, a side effect of how quantum fields behave. The false vacuum was not a flaw. It was simply the state we happened to inherit when the universe cooled. It could last billions of years. It could last forever. or it could vanish tomorrow. The probabilities were astronomically small, but not zero. When Coleman shared his results with colleagues, they reacted with the same mix of awe and disbelief that greets every profound shift in science. Some were terrified. Others were inspired. The idea that the vacuum, the stage upon which all of reality performs, could itself be unstable was almost philosophical. It blurred the line between physics and metaphysics, between the measurable and the unimaginable. Coleman himself remained cheerful. He joked that the end of the universe was unlikely to ruin anyone's weekend plans, since no one would ever know it happened. But behind that humour was the quiet recognition of something vast, that even existence itself may be a temporary arrangement, a balance struck between opposing forces that will one day come undone. In the decades that followed, his idea would become one of the most haunting in modern science. It's known today as vacuum metastability. The notion that our universe might be perched on a ridge, safe for now but not forever. To think of this too literally can be unsettling, so let's return to metaphor. Imagine a candle flame, steady and soft. It burns because the balance between air and wax and heat is perfect for now. But if the air were to change, if the wax cooled or the flame flickered just so, it would go out. The candle wouldn't suffer, and the darkness wouldn't notice. The change would be simple, natural, and complete. That's how Coleman saw the universe. A delicate flame, steady for an age, yet resting on conditions that might one day shift. And so, from his quiet office, surrounded by equations that seemed almost to glow in the lamplight, Sydney Coleman looked into the vacuum and saw not emptiness, but fragility. He saw that everything we call reality might be balanced on a shallow shelf, high above a deeper, unseen valley. He never claimed to know if we would fall, but he was among the first to realise that we might. As we drift further along this strange journey, we'll follow that thought where it leads, to the mechanism that could make such a fall possible, and to the haunting image of a universe rewriting itself at the speed of light. The story now leads us deeper into Sydney Coleman's strange realisation, the mechanism by which the universe could, in theory, rewrite itself. The idea seems impossible at first, even absurd. How could something as vast as a universe simply change its state? How could the ground beneath reality, what we call the vacuum, decide to become something else? To understand, we need to step into the quiet, ghostly logic of quantum tunneling. Imagine a small particle trapped inside a box. It bounces between the walls endlessly, unable to escape because it doesn't have enough energy to climb over them. In the classical world, the world of rocks and rivers and sound, that particle would stay confined forever. But in the quantum world, things are less obedient. The particle is not a single point, but a wave, spread out through space like a mist. And waves don't always stop at barriers. They fade, they thin, they pass through. In a small but very real sense, part of the particle's wave leaks through the wall. Once in a while, by sheer probability, the particle will appear outside the box, free. It didn't jump over the barrier. It simply slipped through it, like a ghost walking through a closed door. That is quantum tunneling, the ability of nature to ignore what seems impossible. It's not a trick or an illusion. It's a fundamental property of the universe, one that allows the sun to shine and the atoms in your body to exist. Every second, inside the hearts of stars, hydrogen atoms fuse into helium not because they have enough energy to overcome their mutual repulsion, but because their quantum waves overlap and merge. The universe, in this sense, survives by its own disobedience. Coleman took that same principle and extended it to everything. If a single particle can tunnel through a wall, he reasoned, then so can an entire field. The Higgs field, which defines the structure of reality, could tunnel from one energy state to another. It might not climb over the barrier separating the false vacuum from the true one. Instead, it could simply pass through, changing state without crossing it in any conventional way. And if that ever happened, a new kind of bubble would form, a small region of space where the Higgs field had reached its lower, truer energy level. Inside that bubble, the rules of physics would be different. The masses of particles, the strengths of forces, even the shape of atoms might change. It would be, quite literally, a new universe budding within the old one. At first, that bubble would be microscopic, smaller than an atom, but the laws of physics favour lower energy states. The new vacuum would be more stable than the old, and so the bubble would grow, feeding on the energy difference between the two states. It would expand outward at nearly the speed of light, consuming everything in its path. There would be no explosion, no visible sign, no warning. The edge of the bubble would move too fast for any signal to escape. One moment, you'd be here, thinking about tomorrow's plans. The next, the concept of tomorrow would no longer exist. Even time itself, as defined by our current universe, would vanish inside that wave of transformation. Coleman described the process with an eerie calmness. In his papers, he wrote as if outlining a recipe for something mundane, but hidden between the lines was the enormity of it all. We would have essentially no warning of its approach, he said later in conversation, the understatement hanging in the air like a sigh. To make this more tangible, imagine a sheet of ice floating on deep water. The ice is solid enough for you to walk on, yet beneath it lies a liquid, colder and denser. Now imagine that a small patch of the ice suddenly melts. That melted spot will spread, not because the ice around it wants to change, but because the liquid underneath is more stable. Soon the whole surface gives way, and the world above it collapses into the depth below. The water isn't evil, and the ice wasn't broken. It was simply the way the system was meant to evolve. That's what vacuum decay would be. An immense melting of reality, where everything we know dissolves into a different form of space. Not destruction exactly, but replacement. The beauty of Coleman's insight was that it didn't require superstition or cataclysm. It arose naturally from the same equations that explain chemistry and sunlight. The possibility of decay was not a cosmic punishment. It was a quiet option, written into the code of existence itself. He calculated the probability of such an event using the tools of quantum field theory, and the numbers were reassuring. The odds of vacuum decay happening in our observable universe were vanishingly small, so small that even in timescales longer than the current age of the cosmos, it was unlikely ever to occur. But unlikely is not impossible, and that single distinction is what gives the idea its haunting power. In the decades that followed, physicists refined his work, introducing corrections for gravity, expansion, and the influence of other fields. They concluded that the Higgs field, given the masses we've measured for it and the top quark, probably does sit in a metastable state. That means it's stable enough to last longer than the age of the universe, but not forever. Someday, perhaps after uncountable eons, a tunneling event might occur somewhere in the cosmic void, and when it does, the final bubble will begin its silent race across the universe. But there is a strange kind of comfort in this too. The process, if it ever happens, would be instantaneous for anyone inside. There would be no pain, no warning, no fear, because there would be no one left to feel those things. The universe would simply transition from one pattern to another, like a note-shifting key in a melody too vast to comprehend. Coleman's students later said he spoke of the idea with a sort of amused detachment. He seemed to find peace in the symmetry of it all. The same quantum laws that allow us to exist also contain the seeds of our end. It was, to him, another example of nature's consistency, the perfect fairness of physics. The universe offers existence freely, but it owes no guarantee of permanence. To many, this thought feels dark. But Coleman found beauty in it. In a universe that began from fluctuation and chance, it seemed fitting that it might end the same way, not in fire but in transition. The cosmos would not explode or vanish. It would simply change its definition of normal. And perhaps that is the most human way to think about it. We too are temporary arrangements of energy, patterns that persist for a while before dissolving. In that sense, the universe's story mirrors our own, a brief moment of order floating in a sea of possibilities. As we drift further into this thought, the horizon opens to a quiet question. If a bubble of new physics ever appeared, what would it contain? Would it hold light, structure, or time as we know it? Or would it be something completely alien? A realm where even the idea of existence has to be reimagined. That is the world we're about to step into next. The universe inside the bubble, a place that might already exist somewhere beyond our reach. The path now carries us beyond the horizon of imagination, into the quiet and unseeable space that Sydney Coleman's equations whispered about, a place inside the bubble. If the Higgs field were ever to fall into its true vacuum, that bubble would expand outward at the speed of light, unstoppable and silent. But what would it be like inside that bubble? What would remain of the universe that once was? We can only speculate because no signal, no memory, and no observer could ever survive the transition. Yet we can think, gently, almost poetically, about what the laws of physics suggest might happen there. Inside the bubble, the Higgs field would take on a new value. You don't need numbers to understand what that means, just imagine that the texture of space changes. The invisible medium that now fills every point of the cosmos would acquire a different thickness, a different kind of drag. The resistance that gives particles their mass would no longer be the same. Electrons might become heavier or lighter. Quarks might refuse to bind. The strength of the forces that hold atoms together could shift just slightly. And those tiny changes would unravel everything. Think of reality as a song played in perfect balance. Gravity, electromagnetism, the strong and weak forces all tuned in harmony. Inside the bubble, that tuning would be broken. The instruments would still exist, but their strings would be too tight or too loose. The melody of existence would collapse into discord. Atoms, if they could form at all, would be different, perhaps unstable, perhaps so tightly bound that chemistry could never emerge. The colours of light would change, because colour itself depends on how electrons dance around nuclei. What we see as blue, green and red are simply the allowed steps in that dance. Change the rules, and the dance stops making sense. Maybe light itself would lose its meaning. Perhaps in that new vacuum, photons could no longer travel freely. The concept of speed of light might not exist. Space could be more rigid or more fluid than anything we can picture. It might collapse on itself or stretch infinitely, no longer caring about balance or form. Even time would not survive untouched. In our universe, time is measured by the steady ticking of processes, the oscillations of atoms, the decay of particles, the movement of stars. Inside the bubble, if those processes fail, there is nothing left to count. The very idea of before and after could fade, replaced by something that doesn't resemble flow at all, just a static, eternal now. It's tempting to imagine the bubble as a sphere of darkness sweeping through the cosmos, but the reality, if we can call it that, would not be black or bright. It would be something entirely other. The physics of that bubble would not know us, not because it hates us, but because it cannot recognize what we are made of. A photon born inside it would have no memory of our sky. A quark there would not know the comfort of confinement. Even the concept of temperature might vanish, because heat and cold only exist in worlds where matter can vibrate, where energy can flow. Inside the true vacuum, there might be no flow at all. Coleman and his collaborators tried to describe this transition mathematically, using smooth, spherical solutions that showed how a new vacuum might nucleate and expand. But beyond the symbols and surfaces, The deeper truth was almost philosophical. If such a bubble ever formed, it would not destroy the universe in the way we imagine destruction. It would overwrite it. The canvas itself would be replaced, and the colours that once painted galaxies and life would never have existed in the new frame. That thought can sound terrifying, but there is a strange serenity in it too. The universe, in this scenario, does not end in suffering or chaos. It ends in transformation, a rewriting of the laws that define what real means. The transition would be perfectly smooth from the perspective of the new physics. It would simply be what happens next. For us, there would be no warning. The bubble's edge, racing outward at light speed, would leave no time for recognition. The distance between now and never would vanish. One moment, the sun would be shining, the oceans turning beneath the wind, the neurons in your mind quietly firing. The next, there would be nothing left to describe those things, no framework for meaning, no concept of things at all. It's easy to imagine that as annihilation, but perhaps it's better to think of it as evolution on the largest possible scale. The universe is not static. It has changed before, profoundly. Once, everything was radiation and energy. Later, it cooled into atoms, then stars, then life. Perhaps one day it will take another form, one we cannot yet conceive. In that sense, the vacuum decay Coleman described could be seen as the next great transition. The same kind of cosmic creativity that has always defined existence. From our limited perspective, it feels like an ending, but from the universe's perspective, it might be just another beginning. The thought invites a curious kind of peace. You are, at this moment, part of a delicate arrangement of fields and forces that has lasted for billions of years. Every heartbeat, every breath, depends on the Higgs field holding steady where it is. And yet, you don't have to hold it up. The universe has carried you effortlessly through its long stability, and it may continue to do so for longer than memory itself. When physicists speak of this hypothetical new vacuum, they sometimes call it the universe that wouldn't know us. It's an apt phrase. It reminds us that our sense of meaning, of beauty, of significance exists only within the thin shell of conditions that make consciousness possible. Beyond that shell, the universe is silent, not cruel, not empty, just quiet in a way that words cannot describe. So, if the thought of the bubble feels eerie, let it also feel humbling. We live in a world that works, a world where light travels, matter clings, and time flows forward. That balance could have been otherwise. It could have fallen into stillness, or never begun to move at all. The fact that it hasn't, that the Higgs field has remained steady through every moment of history, is a kind of grace. As we follow this path a little further, the focus will turn from fear to perspective. For while the possibility of decay is real in theory, the odds are so small that the universe might outlast every star, every black hole, even the fading of memory itself. What seems like fragility is, in truth, incredible endurance. But before we measure that endurance, it helps to remember where it came from. It was born in imperfection, in a symmetry that broke, in a field that fell, and in a balance that somehow never quite stops holding. The trail of thought now carries us away from the quiet doom of the bubble and towards something softer, something statistical, probabilistic, and, in a strange way, comforting. If the universe truly sits in a false vacuum, perched on a shallow ledge above a deeper valley, how likely is it to ever slip? How fragile is our existence, really? To answer this, we have to think in the language of chance, but not the kind we use in daily life. When we speak of probability in the cosmic sense, we are no longer tossing dice or flipping coins. We are measuring events so rare that they might not happen even once during the lifetime of all the stars combined. The universe plays dice with an infinite number of sides, and it rolls them at a pace slower than thought. The process Coleman described, a quantum tunneling of the Higgs field from one state to another, is not forbidden. It's allowed, but its odds are breathtakingly small. The probability that a patch of space will undergo this transition depends on the shape of the energy landscape and the height of the barrier separating one vacuum from another. That barrier in turn depends on the delicate interplay between two of the universe's most fundamental players, the Higgs boson and the top quark. You can think of them as cosmic dance partners, forever linked in a kind of balancing act. The Higgs field gives particles their mass, but the top quark, being the heaviest of them all, pulls back on the field's stability. It's as if the Higgs stretches the cosmic fabric smooth, while the top quark tugs at it from below. If the top quark were just a little lighter, the Higgs field might rest more comfortably. If it were heavier, the field might already have slipped into instability. Physicists describe this interplay with precision, but we can imagine it more simply. Two invisible weights balanced on a cosmic seesaw. The Higgs sits on one side, the top quark on the other. If their masses were in perfect proportion, the seesaw would tilt gently but never fall. Our universe seems to live in that in-between zone, not perfectly stable, not dangerously unstable, but delicately balanced. The ratio between them, according to the latest measurements, sits near a kind of cosmic threshold. It's just right to exist but close enough to fail. If either mass were only a few percent different, everything, the chemistry of stars, the structure of atoms, even the possibility of life, would collapse into impossibility. That's why physicists sometimes speak of a metastable universe. It's like living on a plateau that could, in principle, crumble into a deeper valley. But the edge is so high and the fall so unlikely that you could walk there for eons without worry. The plateau might not be eternal, but it's vast enough to feel like forever. To grasp how long forever means here, consider this. Even if a bubble of true vacuum were to appear somewhere, it would take longer than the combined lifetimes of countless galaxies before another one appeared. The timescale for such an event is so enormous that the human mind can't truly hold it. We can say numbers like 1 followed by 100 zeros, or 10 to the power of 100, but what does that mean in lived time? It's longer than the heat death of the cosmos, longer than the evaporation of every black hole, longer even than the decay of matter itself. In other words, if the universe were a candle flame, it would likely burn steadily until the wax of time itself ran out. And yet, the idea of metastability remains fascinating precisely because it's not absolute. It introduces a subtle imperfection, a hairline crack in the notion of permanence. It reminds us that even cosmic order is not guaranteed by force, but by chance. The universe doesn't have to be stable, it simply happens to be for now. Coleman found this concept oddly poetic. He understood that quantum physics operates in probabilities, not certainties, and that this uncertainty doesn't make the world less real, it makes it alive. Nothing in nature is perfectly still. Even the vacuum trembles, the fields fluctuate, and the laws of physics hum with quiet motion. Stability, in this sense, is a kind of illusion, an averaging of endless fluctuations that cancel one another out. From a cosmic perspective, that's what existence is, a long and improbable pause in an ocean of possibilities. The universe, by all rights, could have been too unstable to form structure at all. It could have remained a brief, brilliant flash that vanished before atoms ever assembled, and yet it didn't. Somehow the dance between the Higgs and the top quark landed in just the right rhythm for complexity to bloom. That is why some physicists speak with a tone of reverence when discussing these measurements. When the Large Hadron Collider finally weighed the Higgs boson in 2012, the result was about 125 billion electron volts, a figure that placed the universe precariously close to that boundary between stability and collapse. And the top quark's mass, measured at roughly 173 billion electron volts, completed the picture. The numbers fit together like a cosmic riddle that says, you exist, but barely. It's strange to think that two invisible quantities, measured in laboratories beneath the Swiss countryside, could tell us something about the fate of everything. Yet that's how physics works. The very small reflects the very large. By understanding the weight of a particle that flickers for less than a trillionth of a second, we glimpse the possible destiny of the entire cosmos. Still, the story isn't finished. Each new measurement, each refinement of data, nudges the needle slightly, sometimes toward stability, sometimes toward instability. The universe, it seems, is teasing us with ambiguity, as though it prefers to keep its secrets balanced on the edge of possibility. But even if the balance were to shift one way or another, the outcome wouldn't change our lives. Whether stable or metastable, the universe's lifetime is unimaginably long. It has already survived countless cycles of birth and destruction, the forging of stars and the drifting of galaxies. It will survive us too, carrying on in calm silence long after our words, our buildings and our memories have turned to dust. So when we speak of vacuum decay, it isn't to fear it, it's to understand the exquisite balance that allows everything to exist. Every sunset, every heartbeat, every quiet night sky is proof that the Higgs field is still holding, that the dice of the universe keep landing for now, on life. And if you ever find yourself awake beneath the stars thinking about all this, try to feel the comfort in it. The universe doesn't need to be eternal to be extraordinary. Its fragility doesn't diminish its beauty, it defines it. The fact that it could all end in a single quantum sigh only makes this long moment of stability feel more precious. As our journey drifts onward, we'll step away from the realm of theory and return to the human story, to the men and women who built the machines that proved these ideas true, who risked decades of effort to find the Higgs itself, and in doing so confirmed just how delicately the universe is balanced. The trail of clues now leads us from theory to the human hands that turned it into reality, from Sydney Coleman's chalkboards to the steel and circuitry of the largest machine ever built by humankind. It begins in the green hills of Wales, with a boy who would one day give the world the tool that proved the Higgs field was real. His name was Lynn Evans, and among his colleagues he would come to be known, affectionately, as Evans the Atom. Lynn grew up in the coal valleys, where the smell of soot and earth hung in the air, and most people expected to spend their lives working underground. His family couldn't have imagined that their quiet, curious son would one day lead a project buried not in coal, but in light, a tunnel circling beneath the border of France and Switzerland, designed to recreate the conditions that existed only a trillionth of a second after the universe began. As a young physicist, Evans was drawn to particle accelerators. He liked that they were equal parts imagination and engineering, machines that pushed against the edge of the possible. In the 1980s, when the idea of building the Large Hadron Collider first began to circulate, many dismissed it as fantasy. The scale was almost incomprehensible. A ring 27 kilometers around, buried 100 meters below the Alps, cooled to colder than outer space, designed to hurl protons so fast they would complete more than 10,000 laps every second. Evans was not deterred. To him, the LHC was not just a machine. It was an act of faith, a declaration that humanity could understand the foundations of its own existence. It would require thousands of scientists, engineers and dreamers from more than 100 countries. It would cost billions, take decades, and test every limit of patience and collaboration. But for Evans, that was precisely the point. Building the collider was like constructing a cathedral in reverse, not upward toward heaven, but downward into the earth, into the unknown. The tunnels beneath Geneva stretched in elegant curves, lined with superconducting magnets that would guide protons with magnetic fields thousands of times stronger than Earth's own. Those magnets had to be cooled with liquid helium to just above absolute zero, making the machine one of the coldest places in the universe. When the protons finally began to circle in opposite directions, each beam carried as much energy as a speeding train, yet focused into a thread thinner than a human hair. When they met, they collided with such intensity that, for an instant, the energy of the Big Bang was reborn. Small flashes of creation repeated 50 million times a second. All of this was orchestrated by Evans, a man with the calm patience of someone who has learned to trust complexity. He once described the project as a bit like conducting a symphony where every instrument is invisible and half of them are from different centuries. The humour was gentle, but it revealed a truth. The LHC was not just a scientific endeavour, but a masterpiece of global cooperation. By 2008, after decades of planning, the machine was ready. The world watched as Evans and his team prepared to switch it on. Newspapers ran dramatic headlines about potential dangers, wild speculations that the collider might create miniature black holes or tear space-time. Some feared the very kind of vacuum decay Coleman had once described. When the day arrived, Evans stood in the control room surrounded by screens, each displaying a cascade of numbers, graphs, and glowing lines. The first protons were injected, and the magnets hummed softly. The beams began to circle, accelerating toward light speed. Cameras clicked, reporters whispered. Then, with a flick of a switch and a ripple of applause, the Large Hadron Collider came to life. Outside, nothing changed. The sky didn't darken, the earth didn't tremble. The air remained still. Inside, though, protons were colliding at unimaginable energies, releasing bursts of new particles that would reveal the inner architecture of the universe. Evans smiled when asked about the fears. Not even a coffee cup trembled, he said. It was the kind of understatement that made his colleagues laugh. Beneath the humour, though, was something profound. The experiment had worked. Humanity had looked into the deep machinery of the cosmos and found it steady. Still, the collider's true purpose had not yet been fulfilled. It wasn't built merely to smash protons. It was built to find something specific, something delicate, almost mythic. For nearly half a century, physicists had searched for the elusive excitation of the Higgs field, the particle that would prove its existence. They called it the Higgs boson, or, in a fit of journalistic mischief, the God particle. Evans never liked that nickname. He found it too grand, too melodramatic. "It's not divine," he said. "It's just essential." Essential indeed. Without the Higgs, the standard model would be incomplete, a melody missing its final note. Every piece of evidence, every equation, hinted that the particle must exist, but no one had ever seen it. If the LHC could find it, it would confirm the mechanism that gave the universe mass, the same mechanism that made stars and people possible. Evans knew the search would take time. The detectors built to capture the collisions were immense, each the size of a cathedral, and filled with layers of sensors that could record the paths of particles lasting less than a trillionth of a second. These detectors, Atlas and CMS, were the eyes of the LHC, and they would watch billions of collisions in the hope that every once in a while the Higgs boson would appear and decay in just the right way for them to recognize its trace. The work was painstaking, the kind of science that requires both patience and faith. For years, Evans coordinated teams, solved engineering crises, calmed funding disputes, and kept the dream alive through setbacks and skepticism. To him, the collider was not merely an experiment. It was humanity's quiet assertion that even the universe's deepest mysteries could be reached with enough collaboration, curiosity, and care. When people asked him why he devoted his life to a machine buried underground, Evans would shrug and say something disarmingly simple, because there's still something we don't know. That statement carries a special kind of humility. It reminds us that the hunger to know is as old as our species, and that the tools we build, be they telescopes, microscopes, or colliders, are extensions of that yearning. In Evans's case, the machine he built would confirm not just a theory, but a truth about our nature, that even when we suspect reality might be fragile, we still reach out to understand it. And so, under the mountains of Geneva, humanity rekindled a spark of the universe's first light, not to control it, not to weaponize it, but simply to see. As we drift further into this story, those collisions will speak. Among the countless flashes of energy and dust, the faint trace of the Higgs boson will begin to emerge, a shimmer in the data that says softly, "I am here." The story now turns to the moment when theory finally became reality, when the invisible hum of the Higgs field revealed itself for the first time. It didn't arrive in a flash of divine light or a thunderous explosion. It arrived as a whisper, hidden within data, patient and precise. Inside the Large Hadron Collider, protons were moving so fast they completed nearly 11,000 laps every second. When two of them met head-on, they didn't shatter like stones. They dissolved into energy, as if their identities momentarily vanished. From that energy, new particles emerged, fleeting sparks that appeared and disappeared faster than any blink. Most were familiar: electrons, photons, quarks. But sometimes, just sometimes, the collisions produced something heavier, something rare, something that would fade almost as soon as it was born. This was what the scientists were searching for, the faint signature of the Higgs boson, the particle that would prove that the Higgs field truly existed. Imagine standing in a dark forest, listening for a single bird's call amid 1,000 rustling leaves. That was the challenge facing the researchers at CERN. Every second, the detectors recorded millions of collisions, generating more data than all the world's libraries combined. Hidden somewhere within that torrent was the delicate trace they sought, a small, specific arrangement of energy that said, "The field is real." The detectors themselves, Atlas and CMS, were miracles of design. Each was a labyrinth of sensors, layers within layers, designed to catch and measure the tiny fragments that burst from each collision. When protons collided, the detectors didn't photograph them directly. Instead, they traced the aftermath, the curling paths of charged particles, the flashes of light in crystal chambers, the faint heat left behind by particles that no longer exist. Reconstructing what happened was like watching ripples on the surface of a pond and inferring the shape of the stone that caused them. The scientists searched for specific decay patterns, certain combinations of photons and electrons that hinted the Higgs had been there for a moment before it dissolved. The process was statistical, almost meditative. They didn't see the particle itself, they saw its ghost, repeated often enough that slowly the outline became unmistakable. It took years of collisions, calibrations, and cautious optimism. There were moments of excitement, tiny peaks in the data that seemed promising, followed by disappointment when they turned out to be noise. But through it all, the scientists remained patient. They were listening to the universe in its own language, and the universe speaks slowly. Then, in 2012, a pattern emerged. Both Atlas and CMS began to see the same faint signal, a small bump in their graphs that shouldn't have been there unless the Higgs boson was real. The probability that it was a random fluctuation shrank with every new collision. When the significance reached what physicists call 5 sigma, the threshold that marks discovery, the numbers finally said what the scientists had hoped for half a century to hear: the Higgs field exists. At 5 sigma, the world exhaled. The announcement came on a bright July morning in Geneva. The auditorium was packed, and the air felt thick with history. On the screen at the front of the room, the graph appeared. A simple line with a tiny rise, barely visible, yet enough to confirm one of the most profound discoveries in human thought. Peter Higgs, now an elderly man with kind eyes and a shy demeanour, sat quietly in the audience. As the applause began, he took off his glasses, wiped his face, and whispered to a colleague, "I'm rather overwhelmed." Around him, hundreds of scientists clapped, cheered, and cried. For them, the discovery wasn't just about a particle. It was about patience, collaboration, and the human desire to understand. What made the moment so poetic was how understated it was. The Higgs boson didn't roar into existence, it whispered. It appeared not in a single photograph or dramatic flash, but in patterns of probability, in the statistical rhythm of nature's smallest events. It was the quietest triumph imaginable, a discovery measured not in fireworks but in certainty. One physicist later said, "It's the sound of the universe breathing." That's what the Higgs discovery felt like. Confirmation that the vacuum, the very fabric of emptiness, was alive with structure. The implications rippled far beyond physics. For decades, the Higgs field had existed only as an idea, a theoretical patch in the standard model that explained why particles have mass. Without it, the equations describing matter would collapse. But now, with the boson confirmed, the model was complete. The invisible architecture of reality was not just elegant, it was real. And yet, even as the cheers faded, a new question arose. If the Higgs boson exists at this particular weight, about 125 billion electron volts, what does that say about the stability of our universe? That number, as it turned out, was more than a confirmation. It was a clue, because that precise value placed the Higgs field right at the boundary between two possible fates, a perfectly stable universe that could last forever, and a metastable one perched on the edge of a deeper collapse. The discovery that day did not just reveal how we exist, it also revealed how precarious that existence might be. But that realization came later. For now, the scientists celebrated, the world smiled, and Peter Higgs quietly left the auditorium to escape the reporters. As he walked out into the cool Swiss air, he was spotted by a journalist who asked how he felt knowing his life's work had changed science forever. He paused, gave a small, almost embarrassed smile and said, "It's nice to be right sometimes." Then he walked away toward a cafe to have lunch. Inside the collider, the protons kept circling, colliding, glowing for the briefest instants before disappearing. Each collision, each whisper of light, was another affirmation of the hidden structure that holds everything together. It was as though the universe itself had spoken, softly but unmistakably, confirming that even emptiness is full. As we follow the story further, we'll step away from the machines and back to the people, to the man who had imagined this all decades earlier, who found the idea so overwhelming he once fled to a pub to avoid the noise of success. For every great discovery, there is a human heartbeat behind it, steady and shy, reminding us that the universe may be ruled by symmetry, but its explorers are gloriously imperfect. The story now narrows its focus, from the grand, glowing tunnels beneath the Alps to a quiet, dimly lit pub somewhere in Edinburgh. Outside, the summer rain taps gently on the windows. Inside, a man sits alone at a wooden table reading the menu. He orders soup and trout for lunch, a pint perhaps, and opens his newspaper to pass the time. Around him, the low murmur of conversation fills the air. No one notices that the man who just sat down is the reason the world's largest machine was built, or that his idea has just been proven true. His name is Peter Higgs, and this is the day he learned he has changed our understanding of the universe. Higgs had always been a reluctant celebrity. He loved physics for its stillness, its precision, its quiet beauty. Fame, noise, and microphones made him uncomfortable. When the announcement of the Higgs boson discovery went public, reporters swarmed the physics department, eager to capture his reaction. But Higgs was nowhere to be found. He had slipped away without fanfare, walking through the drizzle to his favourite neighbourhood pub. While the world celebrated him, he celebrated a bowl of soup. That image, a man avoiding the limelight on the very day his theory was confirmed, feels deeply fitting. Though Higgs field itself is invisible, constant and omnipresent, yet it makes everything else visible. It doesn't announce itself, it lets the universe speak through it. Peter Higgs was much the same, quiet, steady, almost shy. He had once said he didn't like how people called his discovery the God particle. To him, it was just one part of a larger, elegant whole. Calling it that, he once sighed, makes it sound like we've found something divine, when what we've really found is something profoundly human. The understanding that everything, even emptiness, can have structure. When Higgs first proposed his idea in 1964, it had been met with skepticism. The field he described was unlike anything physicists had seen before, an invisible ocean that filled all of space, giving mass to particles that interacted with it. The equation suggested that without it, the world would be featureless and weightless. But to many at the time it sounded too abstract, too convenient a patch for the gaps in the standard model. One reviewer even rejected his paper, calling it of no obvious relevance to physics. Higgs was not a man who fought back with anger. He simply wrote another version of the paper, expanding the explanation and making the idea clearer. Eventually it was published. Still, few paid attention. He went back to teaching, to his quiet office at the University of Edinburgh, where chalk dust settled on the corners of his sleeves and his notes grew into a modest pile on the desk. He lived through decades of doubt and silence. When the standard model grew more powerful and successful, others began to notice that there was still a gap at its centre, a missing piece that could explain how particles acquired mass. Gradually the community realised that Higgs's proposal, along with similar work by other theorists like François Englert and Robert Brute, might indeed be that missing piece, but the proof would require something beyond imagination, an experiment powerful enough to recreate the conditions of the early universe. Higgs watched as others took up the challenge. He was not bitter, not territorial. Science, he once said, isn't about ownership, it's about understanding. So he waited, quietly, through the years as new machines were built and data was gathered until finally the Large Hadron Collider brought his idea to light. When news of the discovery broke, François Englert called to congratulate him. They would later share the Nobel Prize. Higgs accepted it with grace but little excitement. He was proud, of course, but the attention made him uneasy. When the Swedish Academy called to inform him, they couldn't reach him at first. He had gone for a walk. By the time he returned home, the world's journalists had already gathered outside his door. His neighbours, amused, described the scene as a quiet man suddenly at the centre of the universe. There's something profoundly poetic about that image, the man who revealed the field that gives everything mass sitting alone in a pub, unbothered, drinking his beer. His simplicity matched the nature of his discovery. The Higgs field doesn't force or compel, it simply exists, and by existing, it allows the rest of the cosmos to have weight. It's easy to imagine Sydney Coleman, somewhere in another time, smiling at the irony. Coleman had found the Higgs field's potential weakness, the possibility that it could one day decay, erasing all that it had created. Higgs, in turn, had discovered its strength, the quiet endurance that had held reality together for 14 billion years. Between them lies a perfect symmetry, fragility and stability, coexisting in one elegant system. At the Nobel ceremony in 2013, Higgs stood awkwardly in his tuxedo as cameras flashed. The applause was thunderous, but his expression remained mild. When he stepped to the microphone, he thanked his colleagues, his collaborators, and the countless people who had built the collider. Then he paused. "The lesson of science," he said softly, "is that understanding takes time, sometimes a lifetime." Sitting in the audience that day was another physicist whose story, though less celebrated, carried its own beauty. Abdus Salam, the first scientist from Pakistan to win a Nobel Prize in physics. Decades earlier, Salam had helped build the very theories that made the Higgs mechanism possible. He was known for his bright turban and for his kindness. When he accepted his award, years before, he spoke not of equations but of poetry. "The beauty of the universe," he said, is greater than the pride of nations. The connection between Higgs and Salam is more than academic. They both remind us that science is a human endeavour, carried out not by perfect minds but by imperfect people chasing clarity. Higgs with his quiet humility, Salam with his eloquence and hope. They show that knowledge advances not through ego, but through patience. As we drift further along this quiet reflection, it's worth pausing to consider the irony at the heart of it all. The universe may be ruled by symmetry, by balance and mathematical grace, but the people who uncover those laws are full of asymmetry, flawed, hesitant, passionate, afraid, and curious. And perhaps that imperfection is what makes their discoveries resonate so deeply. Peter Higgs once said that he didn't feel his idea was extraordinary. "I was just trying to make the equations work," he admitted. But that small act of curiosity reshaped the story of existence. So, in that pub on a rainy afternoon, as the world buzzed outside and the soup cooled in its bowl, Higgs sat quietly, not as a hero, but as a man who had glimpsed something eternal and preferred to let it speak for itself. The universe didn't need to roar its secrets into the world, it whispered. And he had been listening. Our story now turns to the delicate numbers that followed, the measurements that reveal the universe's precarious balance, the ratio that tells us how close we stand to the edge of stability. For as much as Higgs gave the universe its mass, those same equations may also reveal its greatest weakness. Our quiet exploration now turns toward a kind of cosmic arithmetic, numbers so small and so vast that they blur the boundary between science and poetry. After the discovery of the Higgs boson, the celebration at CERN began to fade into the steady hum of analysis. The physicists, ever patient, turned from applause to precision. They wanted to know not only that the Higgs existed, but what its exact weight meant for the fate of the universe. You could think of the Higgs boson as a messenger, a tiny ripple that carries news from the invisible field surrounding us. The message it delivers depends on its mass, which determines the shape of that field's energy landscape. The same landscape that Sydney Coleman had studied when he worried about false vacuums and hidden valleys. Now, for the first time, scientists had measured the Higgs mass precisely enough to sketch that landscape for real. The number they found was about 125 billion electron volts. So small it defies intuition, yet so decisive that it shapes the stability of the cosmos itself. But the Higgs doesn't stand alone. It has a companion that complicates everything. The top quark, the heaviest known elementary particle. Its mass, around 173 billion electron volts, tugs at the Higgs field like a weight pulling on a sheet. The two are connected through their interactions, and their balance decides whether the universe is secure or precarious. If the top quark were a little lighter, the Higgs field would rest in a perfectly stable valley. The universe could expand and cool forever without worry. If the top quark were slightly heavier, the Higgs field would sit on a ridge, just one tremor away from slipping into a deeper abyss. Where we actually live is astonishingly close to that boundary, a narrow band between stable and unstable. Physicists call it the metastable region. Imagine walking along a mountain path that's only a few steps wide with cliffs on either side. The ground beneath you feels firm, but one wrong shift could, in theory, send everything tumbling. Yet the path stretches so far ahead that you could walk for billions of years and never reach the edge. That's where our universe sits, balanced, steady for now, but perched on a ridge where the mathematics whisper that it could fall someday. To visualize this, scientists sometimes draw what they call a potential curve, but we can translate that into something simpler. Picture a shallow bowl sitting inside a larger one. The marble representing the Higgs field rests in the smaller bowl. It seems safe enough, there's a rim holding it in place. But beyond that rim lies a much deeper basin. If a strong enough fluctuation ever lifted the marble over the edge, it would roll down into that deeper valley, and the physics of everything would change. The Higgs's measured mass and the top quark's mass together determine the height of that rim. The startling truth is that the rim isn't very high. It's tall enough to hold the marble for an almost infinite time, but not infinitely tall. In other words, our reality is secure for longer than we can comprehend, but not forever. This realization came slowly, through years of refined measurements and recalculations. The physicists who discovered the Higgs knew that its weight mattered, but few expected it to fall so precisely in this narrow window, the one that places the universe right on the edge of metastability. It was as if nature had fine-tuned itself to live in a state of delicate tension, neither completely safe nor immediately doomed. Some found this unnerving, others found it deeply moving. The universe, it seemed, was not the fortress of certainty we once imagined, but a tightrope walk of balance. Everything that exists, galaxies, stars, planets, life, depends on that balance holding. To describe how close we are to the edge, physicists sometimes use analogies. One favourite is to imagine the entire universe as a candle flame. A stable universe is a flame burning clean and steady, never wavering. An unstable one is a flame that flickers wildly before going out. A metastable universe, ours, is the candle that burns perfectly still for eons, yet remains sensitive to the faintest change in the air. It could, in theory, be extinguished by the softest breath of quantum chance. But before we let that image fill us with unease, it's worth remembering how breathtakingly small that chance really is. Even if the universe is metastable, the odds of a vacuum decay event happening within the next trillion years are so tiny that they may as well be zero. The timescales involved are beyond comprehension, far longer than the lifespan of every star that will ever form. In a sense, metastability is as good as stability. The candle may tremble in theory, but in practice, it shines calmly through eternity. And perhaps that's what makes the discovery of the Higgs boson even more beautiful. It's not just proof of how the universe gives itself mass. It's a reminder of how delicate, how precisely balanced that process is. The numbers we measured could have been anything. They could have placed us in a stable universe, or a collapsing one, or a universe that never allowed atoms to form at all. Instead, they placed us here, on the knife's edge, safe enough to breathe, fragile enough to wonder. It's as though the universe wanted to remind us that certainty is an illusion, and that beauty often resides in the space between perfection and collapse. We're not floating in a fortress of absolute laws. We're drifting on a raft of probabilities, buoyed by a balance we can neither control nor fully explain. One might ask whether this fine balance hints at design or meaning, but perhaps the better answer is humility. The universe doesn't need intention to be miraculous. It only needs to be improbable, and to last long enough for someone to notice. Peter Higgs, when asked about the implications of the metastability result, smiled faintly and said, "I don't think the universe is in any danger." Then, after a pause, he added, "But if it were, there'd be no one left to worry about it." It was his usual blend of humour and modesty, the acknowledgement that science often reveals our smallness more than our power. So here we stand, at the intersection of precision and wonder, knowing just enough to realise how precarious it all is. The Higgs boson's quiet weight and the top quark's invisible heft have told us something extraordinary. That our universe is neither perfectly safe nor catastrophically doomed. It is balanced, steady for now, like a candle flame that flickers not from fear, but from the breath of possibility itself. And as we drift onward into the last part of our journey, we'll turn from the numbers back to meaning, to what this fragile balance tells us about our place in the cosmos. Because understanding that the universe could change doesn't make it less beautiful. If anything, it makes every moment of stability, every breath and heartbeat, feel like a small miracle of endurance. Our quiet exploration now drifts into a place between awe and unease, a moment to look up at the night sky and feel both wonder and humility. The ancient philosopher Cicero once told a story about a man named Damocles. He envied the king's fortune, so the king invited him to a feast, giving him gold, wine, and music. But above his head, the king hung a sword, suspended by a single horsehair. Damocles soon realized that wealth meant nothing when danger hung invisible above him. He asked to leave the throne and return to his simple life, for he had discovered the weight of uncertainty. In many ways, the universe lives beneath its own sword, a vast cosmos balanced delicately between stability and collapse, held by a single thread of probability. Sydney Coleman's equations were the first to reveal that thread, the possibility that our reality might one day shift, silently and without warning, to a new state of being. The sword would not fall with thunder or flame, it would descend softly, faster than light, rewriting the laws of physics as it passed. It's an unsettling thought, isn't it? That the same calm emptiness we gaze into at night could hold such potential, such quiet power. Somewhere, perhaps unimaginably far away, the vacuum could be trembling ever so slightly, preparing for a change we would never see coming. A single ripple in the vast ocean of space-time could begin its journey, invisible, unstoppable, expanding outward through the dark. Coleman spoke of this possibility with calm precision, but behind the mathematics was something almost poetic. He knew that in such a universe fear was meaningless. If the bubble of true vacuum ever formed, we would never know it. There would be no pain, no moment to realize, no shadow to flee. The edge of that bubble would move at light speed, and everything it touched would simply transform into something new. The sword above the cosmos may hang forever, or it may fall in perfect silence. Either way, there is peace in knowing that the fall, if it comes, would be kind. When you imagine that bubble, expanding, invisible, rewriting reality, it's easy to feel small, but smallness isn't weakness, it's perspective. To be small in a universe this vast is to recognize our place within its balance. The cosmos isn't cruel. It's indifferent, yes, but in that indifference lies a strange serenity. The vacuum hums, the stars burn, and you, sitting here, are made from the same forces that could one day fade. That knowledge isn't meant to frighten, it's meant to awaken gratitude. Perhaps this is what Coleman himself understood as he wrote his final words on the topic. He knew that to live in an unstable universe is not a curse, but a privilege. To exist in the brief calm between possibilities. After all, the Higgs field could have taken a different path. The early universe could have cooled into chaos or failed to form atoms at all. Instead, it settled into this improbable equilibrium, a balance that has lasted long enough for stars to be born, for life to emerge, for consciousness to wonder about its own impermanence. Imagine a lake at night, perfectly still. Beneath its surface, tiny ripples move unseen, disturbances too small to break the reflection of the moon. That's what vacuum metastability feels like. Beneath the calmness of existence, there are fluctuations, quantum tremors that never quite disturb the surface. Every once in a while one might grow large enough to ripple the entire lake, but it hasn't happened, not yet. And perhaps that stillness is the point. There's something beautiful in knowing the universe doesn't need to last forever to be meaningful. The sword above us is not a threat. It's a reminder that even the cosmos with all its galaxies and nebulae and roaring suns is delicate. Its strength lies not in permanence but in endurance. Like a violin string stretched tight, it vibrates in harmony precisely because it could break. The possibility of failure gives the melody its sweetness. When you think about it that way, our fragility connects us to the universe rather than separates us from it. The same principles that govern the decay of fields also govern the beating of hearts, the flicker of thought, the rise and fall of civilizations. Everything that exists carries within it the potential to change, to end, or to begin again. The sword above the cosmos is the same sword that hangs above each moment of our lives, the quiet awareness that nothing is guaranteed and that this makes every instant precious. In that awareness, fear dissolves into wonder. If the universe is fragile, then so are we, and that shared vulnerability becomes its own kind of beauty. We survive not because we are strong, but because we exist within a balance that somehow holds. This same physics that allows a Higgs field to hum in steady patience also allows a person to love, to imagine, to reach for meaning even in uncertainty. So when you hear the phrase vacuum decay, don't picture destruction. Picture transformation. Picture a wave passing through the dark sea of reality, leaving behind not ruin but change. The universe, after all, began with a transformation, an explosion of symmetry breaking that gave birth to everything. If another transformation were ever to come, it would be part of that same grand rhythm, the same unfolding story. Coleman once joked that if the vacuum ever did decay, at least no one would have to pay taxes the next day. It was his way of reminding us that worry is wasted on the inevitable. You can't outrun probability, but you can live joyfully within it. The sword above the cosmos doesn't demand fear, it asks for appreciation, for the chance, however brief, to exist beneath a universe that works. As you sit here now, surrounded by the quiet hum of life, your breathing, the faint sounds of the world around you, remember that the same Higgs field that shapes the cosmos also passes through you. It gives weight to your body, substance to your thoughts. You are, in a very literal sense, a vibration within that field, a part of the same fragile miracle. And so, we live, knowing the sword may never fall, and finding comfort in that knowledge. The universe has held for 14 billion years. The thread above it may be thin, but it has never broken. Perhaps that is what makes existence luminous. Not the promise of eternity, but the grace of continuation. As we drift further along this final path, we'll turn from the cosmic to the personal, from the fragility of the universe to the fragility that defines every breath and heartbeat. Because what we fear in the vacuum's decay is not the end of the cosmos. It is the reflection of our own impermanence. As we follow this thought further, the vastness of the cosmos begins to fold inward, returning to something smaller, more familiar. We've wandered through probabilities and fields, through invisible tremors in the vacuum and the soft hum of the Higgs. But now, the story gently turns towards something quieter. What this fragility means, not just for physics, but for us. We often imagine that strength and permanence are what give things value. We treasure the mountain because it endures, the diamond because it does not break. Yet when you look closely, it's the fragile things that make life beautiful. A snowflake, with its lacework of symmetry, lasts only a breath before melting. A flower blooms and fades within a season. Even a heartbeat, the simplest rhythm of all, is fragile, repeating faithfully only for a while. Perhaps the same truth holds for the universe itself. The same equations that give rise to stars also contain the possibility of their undoing. The same field that allows matter to exist also holds the potential to erase it. The same laws that make life possible guarantee that it will one day end. Fragility isn't a flaw in the design, it is the design. Sydney Coleman understood this in his own way. His discovery wasn't a prediction of doom, but an acknowledgement of the universe's honesty. Nature doesn't hide its weaknesses. It lays them bare, woven into the same fabric that makes it strong. Every atom, every field, every particle carries both creation and decay within it, perfectly balanced. That balance is what makes existence dynamic rather than static. And perhaps, when you think about it long enough, you realise how deeply human that is. We too are creatures of temporary structure. Our bones may seem solid, but they shift and weaken with time. Our memories fade, our voices soften. And yet, within that fragility lies compassion. to know that things end is to love them more deeply while they last. The physicist Emmy Noether, whose work connected symmetry to conservation, once showed that every lasting quantity in nature, energy, momentum, charge, arises from a hidden symmetry. But when symmetry breaks, new possibilities appear. The Higgs field itself was born from such a breaking. When the universe cooled and perfect symmetry fell apart, diversity emerged. Forces separated, particles gained mass, and complexity bloomed. It's a lovely irony. Perfection is sterile. Imperfection creates. Fragility gives the universe its texture, its variety, its story. Without it, there would be no galaxies, no chemistry, no life. The fall from symmetry is what made beauty possible. In that sense, the weakness we find in the vacuum is not something to mourn. It's a cosmic reflection of our own vulnerability. The Higgs field hums, unstable yet steady, just as we live, uncertain yet determined. The universe persists through delicate balance, and so do we. You can see this truth everywhere if you look gently. In the way soap bubbles shimmer for a moment before bursting, in the way sunlight filters through dust, turning imperfections into gold, in the way a thought appears in the mind and then vanishes, leaving only warmth behind. Fragility in all its forms is what makes the moment luminous. Even stars live by this rule. They burn because of an unstable equilibrium, gravity pressing inward, radiation pushing outward. That tension keeps them alive, but it also ensures their eventual death. Every sunrise you've ever seen is powered by this quiet instability, by the same delicate physics that governs the Higgs field. The universe shines not because it's unbreakable, but because it's on the verge of breaking beautifully. There's comfort in that realization. It means that weakness and beauty are not opposites. They are partners. The candle flame is gentle precisely because it can be extinguished. The laughter you share exists because it can end. The fragility of life is not an accident to be fixed, but a rhythm to be cherished. When you breathe, you participate in that rhythm. You inhale stability, the repetition, the continuity of things. You exhale impermanence, the release, the letting go. That simple act mirrors the physics of the cosmos, expansion and collapse, formation and decay. Each breath is a small version of the universe's own balance, a reminder that endurance is not the absence of fragility, it's its expression. Perhaps this is why, when we look up at the night sky, we feel something that isn't quite fear and isn't quite comfort. We sense that everything around us, every photon, every atom, is living on borrowed time, yet still managing to shine. We are witnesses to a grand and fleeting masterpiece, painted in light that will one day fade, but not yet. Peter Higgs once said that when he thought about his field's possible instability, he didn't find it tragic. The field could change, he said, but it hasn't. To him, that was enough. Existence didn't need permanence to be meaningful. The meaning came from the fact that the field had endured long enough for us to notice. That's the heart of it, really. The universe's weakness is also its poetry. Its precariousness is what gives rise to gratitude. We are not living despite fragility, we are living because of it. When you hold a snowflake in your palm and watch it melt, you don't mourn its end. You marvel at the brief perfection it achieved before it disappeared. That is how we might learn to think of everything. The stars, the galaxies, even ourselves. Not as permanent monuments, but as moments of astonishing balance, here just long enough to be beautiful. And just as the Higgs field allows particles to have mass, to resist motion and form substance, perhaps our own fragility allows us to have meaning. If we were eternal, unchanging, untouched by loss, we would have no need for love or kindness or memory. The tenderness of being human, of existing in a universe that might someday wink out, is its own kind of miracle. So, as you lie beneath the quiet weight of the night, remember this. The stars above you are fragile too. They shimmer for billions of years, but even they will one day fade. The same equations that make them burn will one day cool them into silence. Yet for now, they are there. The Higgs field holds, the vacuum hums. The universe, delicate as it is, remains intact. And maybe that's the true meaning of fragility. Not something to fear, but something to thank. For it is only through the possibility of ending that anything ever begins. As we drift further toward the close of our story, we'll turn from this understanding to comfort, to the reassurance that, in all likelihood, the universe will hold for longer than memory itself. The sword may hang, but its thread has proven astonishingly strong. Our quiet journey now turns toward reassurance, the soft exhale after all the wondering. By now you've heard how the universe might, in principle, one day change completely. You've seen the fragile thread that holds existence together, the sword that hangs above the cosmos by a single strand of chance. And yet, the truth is gentler than the image suggests. You can rest easily tonight, because the universe has proven itself to be astonishingly patient. Let's begin with a small and comforting fact. The chance that vacuum decay will happen anywhere near us, within the lifetime of every star that will ever exist, is so close to zero it might as well be called impossible. Even the most cautious physicists, those who spend their lives calculating cosmic risks, agree that if the universe is metastable, its lifetime is longer than 10 to the power of 100 years. That's a 1 followed by 100 zeros, a number so vast that it dissolves the imagination. In that stretch of time, every black hole will evaporate, every atom will disassemble, and still the Higgs field would likely remain unshaken. So even though we know the universe sits delicately on a ridge, the ridge is wide enough to walk for eternity. If vacuum decay were ever to begin, it would start somewhere far beyond our sight, perhaps in a corner of the cosmos where space is emptier and colder. A single quantum tremor might nudge the field into its lower state, birthing a bubble of true vacuum. But that bubble would expand at the speed of light, meaning it would reach us at the same instant we became aware of it. There would be no fear, no pain, no warning, just a seamless transition to something else, faster than thought. In that sense, the end, if it comes, is perfectly kind. The universe would not end in agony or fire. It would end in silence, in the gentlest way possible, by changing form. We would never know. It would be like closing your eyes at night and never realizing the dream had begun. This is why physicists often speak of the vacuum's instability, not with dread, but with fascination. It's a theoretical curiosity, a mathematical whisper, a way to probe how finely the laws of nature are balanced. The equations that describe this process, beautiful but intimidating on paper, can be translated into something far more comforting in words. The probability is vanishingly small. The candle flame will burn long after the stars have gone out. And perhaps the deeper truth hiding in all this is that we were never meant to control the fate of the universe anyway. Our task isn't to outlast it. Our task is to be awake while it lasts, to notice, to marvel, to live. Think about that for a moment. Every field, every atom, every breath you take depends on a perfect equilibrium that has held for over 13 billion years, and it continues to hold, silently, effortlessly. You don't have to hold it together, it holds you. You are part of its balance, a quiet ripple in its ongoing patience. Even if one day the universe transforms, it doesn't erase what came before. The patterns of energy that make up your body, your thoughts, your laughter, they don't vanish in the deepest sense. They change form, continuing the story in ways you or I could never perceive. The matter of your body is older than the sun. The carbon in your blood was forged in a star that died billions of years ago. And when you are gone, those same atoms will continue their slow drift through the cosmos, waiting to become something new again. In that way, You are already eternal, not as a person, but as presence, as movement within the vast continuity of things. The universe doesn't need forever to make that true. It only needs this moment. The beauty of physics is that it shows us just how improbable and temporary existence is, yet how utterly stable it feels from the inside. You wake, you breathe, you move through the world, and everything seems fixed and familiar. The atoms in your body hum with quiet confidence. They don't know about vacuum decay or metastable states. They just continue, doing what they've done since the beginning of time, obeying the laws that have never failed them. When you step outside and look at the night sky, you're looking into reassurance. The same stars that watched over ancient civilizations still shine, their light crossing oceans of time to reach you. The cosmic background radiation, the faint afterglow of the Big Bang, still hums at a temperature just above absolute zero, constant and undisturbed. The universe is not trembling, it is calm. The thought of fragility only reminds us that the calmness is real. Like a glass window that seems delicate but holds against every storm the cosmos endures. It may have weaknesses written into its structure, but those weaknesses are not cracks. They're harmonies. They make the melody richer. They remind us that even permanence needs a touch of uncertainty to feel alive. And so, we can sleep peacefully. Not because the universe is safe in an absolute sense, but because it is patient beyond all need for worry. The Higgs field hums, the stars burn, the laws of physics remain constant. You have nothing to fear from the silent balance that sustains you. In a way, vacuum decay, the most dramatic ending imaginable, is also the kindest. It's the universe's way of promising that if change ever comes, it will come without suffering, without alarm, without regret. A soft turning of the page, a new story written in the same ink of existence. Until then, you have this moment, this breath, this heartbeat. You have the candle flame that continues to burn, the sound of the world still unfolding. You have the chance to notice it, to let it fill you with quiet gratitude. So if you find yourself lying awake under the stars, wondering about the universe's great weakness, know that it isn't really a weakness at all. It's a reminder of strength disguised as impermanence. The fact that the universe can be fragile yet endure for billions upon billions of years means that fragility and stability are not opposites. They are two sides of the same truth. The Higgs field could have collapsed 1 trillion times by now, but it hasn't. And that endurance is what allows everything you love to exist. You can close your eyes knowing that the sword above the cosmos is held steady since before there were stars to reflect its edge. It will likely remain hanging long after every star has gone dark. The thread may shimmer, but it does not break. And as you drift towards sleep, you can imagine that same field, still humming softly through the atoms of your body, through the air, through the night itself. It holds you in its quiet, patient embrace, just as it holds the galaxies and the light of faraway suns. You're safe inside that hum, part of its calm continuity, sharing its vast and ancient peace. And so, we arrive at the edge of the story, the quiet moment where science turns back into wonder, and the universe feels less like a machine and more like a dream that somehow learned to last. We've followed particles through fields, walked along the ridges of probability, and stood beneath the sword that may hang forever above the cosmos. Now, as the echoes fade, it's time to rest in what remains, the understanding that existence itself is the gentlest kind of miracle. Sydney Coleman, the physicist who dared to imagine that the vacuum might one day decay, used to smile when people asked if he found the idea frightening. "Not really," he said, "because if it happens, you won't even notice." Beneath the humour was wisdom. He wasn't mocking fear, he was reminding us of proportion. The universe has never been a place for panic. It has always been a place for patience. Coleman spent his life looking into the heart of uncertainty, and found beauty there. He taught that a world can be meaningful even if it is temporary, that maybe it's meaningful because it's temporary. His equations hinted that the ground beneath everything could shift someday, but his laughter suggested that such knowledge only deepens the joy of being here now. And then there was Peter Higgs, whose own quiet discovery made Coleman's question possible. Higgs showed us that what we call emptiness isn't truly empty. It's filled with an invisible field that gives substance to everything. Without it, there would be no mass, no structure, no stars, no breath. The Higgs field is the thread that ties the universe together, not by force, but by presence. Like the air that holds a feather aloft, or the silence between notes that makes the music whole. Finally, there was Emmy Noether, who long before either of them had shown that symmetry lies at the heart of nature's order. She proved that for every balance in the universe there is a conserved truth, energy, motion, charge, all enduring because of deeper harmony. Her work became the hidden foundation of everything that came after. She never sought fame, but her ideas lived quietly in every discovery that followed, connecting beauty and vulnerability, order and imperfection. These three, Coleman, Higgs, Noether, never worked together, yet their thoughts intertwined like three strands of light. One revealed the possibility of change, another revealed the field that makes existence possible, and the first revealed the laws that ensure those patterns hold. Together, they remind us that science is not a cold pursuit of certainty, it's a love letter to the unknown. And you, listening now, are part of that same continuum. You too are made of the Higgs field's hum, of atoms that learn to dance because a symmetry once broke, and because a field once fell into place. Every particle in your body carries the faint memory of that first transition, the one that gave the universe weight and form. The calcium in your bones was forged in the cores of stars, the oxygen in your lungs in the collapse of those same stars, the carbon in your blood from the ashes that followed. You're a tapestry of cosmic fragility, stitched together by the persistence of balance. When you breathe, you're proof that the Higgs field still holds steady. When you think, your neurons fire with the same quantum forces that guide starlight through space. You're not separate from the cosmos. You're one of its quiet experiments, a local expression of its desire to understand itself. Sometimes, late at night, scientists at observatories pause between calculations and simply look out at the stars. The data will always wait, but the feeling of seeing the universe and knowing you're inside it, that cannot be postponed. It's the same feeling that draws poets to write and children to ask why the sky is blue. Curiosity, that small flicker of wanting to know, may be the universe's most profound creation. The fragility of the cosmos is not something to fear, it is something to cherish. Because fragility gives rise to care, to the instinct to protect, to nurture, to remember. It's what makes us hold each other a little longer, speak a little softer, notice the quiet things. If the universe were invincible, perhaps we would take it for granted. But knowing that it could, in theory, one day change, teaches us to value every instant it remains as it is. Look around your life for a moment, the small things that endure despite time's pull. The way light filters through a curtain in the afternoon, the sound of rain on rooftops, the warmth of another person's hand. These are not separate from physics, they are its living consequences. Each is built upon that same web of interactions, those same balances that began when the Higgs field first settled and symmetry gave way to form. And though the field may not be eternal, it has been faithful. 14 billion years of holding atoms together, of resisting collapse, of keeping the flame of matter alive. Whatever future may await the universe, this age, our age, is proof of its patience. Perhaps someday, long after our kind has vanished, the universe will move on to another chapter. The Higgs field may fall into a deeper valley, rewriting its laws, erasing what came before. But even if that happens, it won't be an end. It will be a continuation of creation, the way a seed must break for a tree to grow. Reality will fold into something new, and that too will be beautiful in its own way. For now, though, the field holds. The universe is steady, the atoms still hum, the candle flame still glows, and you are still here. That is enough. As you rest tonight, remember that you are part of something immeasurably ancient and unimaginably delicate. You exist because the laws of physics found a way to balance chaos and calm. You endure because the universe, fragile though it may be, endures with you. And so, as this quiet story draws to a close, let the last thought settle gently. The universe may be temporary. Reality may one day fold into something new, but for now, the Higgs field holds, and that is enough. If your eyes are still open, thank you for staying through this quiet journey. And if they're closed, may the universe hum softly around you, stable, serene, and full of wonder. Good night.